From hydrogen to fireballs, the origins of stars. Before we drift into the cosmic nursery where stars are born, tell us in the comments, where are you watching from tonight? Are you beneath a sky full of ancient light, or perhaps in a city where the stars play hide and seek behind the glow? We love knowing that this story of stellar birth is reaching you wherever you are in this vast star-filled universe. Let us know your corner of the cosmos. You drift through the cosmic nursery, where darkness is not empty but pregnant with possibility. You feel the weight of hydrogen clouds older than memory, whispering secrets in a language that atoms haven't learned to speak yet. The cold embraces you, not the cold of winter, but the cold of waiting, of becoming. Here, in the spaces between what will someday be called galaxies, you float through a silence so profound it has texture, so complete it feels like the held breath of the universe itself pausing before its next great exhale. This is the era cosmologists call the Dark Ages, though darkness here is not absence but anticipation. The universe has cooled enough for hydrogen atoms to form, their single electrons dancing around lone protons in the cosmic waltz that will define the architecture of everything to come. You move through clouds of this primordial hydrogen, vast beyond comprehension, stretching across light years like the dreams of sleeping giants. These are not the empty spaces that human eyes see when they look up at night. These are the wombs of stars, the stellar nurseries where gravity first learned to sculpt with invisible hands. The temperature here hovers just above absolute zero, barely warmer than the cosmic microwave background that bathes all of space in the afterglow of creation. Yet within this cold, something stirs. Quantum fluctuations, the universe's own heartbeat, create tiny variations in density, regions where hydrogen atoms cluster just slightly more densely than their neighbors. These are the seeds, the first whispered suggestions that not all of space will remain uniform forever. You drift through these density variations like moving through the thoughts of a dreaming cosmos, each fluctuation a potential star, a future sun waiting in the quantum foam of possibility. The hydrogen around you is mostly neutral protons and electrons paired in matrimonial stability, content in their atomic completeness. But here and there, cosmic rays and the fading radiation from the Big Bang itself ionize some of these atoms, stripping electrons from their protons and creating a sparse plasma that shimmers with barely perceptible electromagnetic fields. This ionization creates a kind of cosmic weather, invisible storms of charged particles that will help shape the formation of the first stellar nurseries. You are witness to the universe's childhood, to the moment when matter first began to organize itself into patterns that would eventually become the cosmic web, that vast scaffolding of dark, matter and hydrogen, along which galaxies would string themselves like luminous pearls. The silence here is not merely the absence of sound, but the presence of potential. Every hydrogen atom carries within it the possibility of fusion, the dream of becoming helium, the aspiration to burn with stellar fire. Yet they wait, scattered and patient, for the cosmic choreographer called gravity to gather them into the dense embrace necessary for nuclear ignition. You float among billions upon billions of these atomic actors, each one a future participant in the stellar drama that will illuminate the cosmos and forge the elements that will someday become planets, oceans, and the very neurons firing as you contemplate this moment. In this pre-stellar epoch, the universe is democratic in its darkness. No star has yet claimed dominance over any region of space. No sun has carved out a solar system as its domain. The hydrogen clouds stretch in every direction, their boundaries fluid and negotiable, interpenetrating like the overlapping dreams of cosmic entities. You drift through regions where the density is slightly higher, feeling the first tentative pull of what will eventually become gravitational wells, the invisible valleys in space-time where matter will eventually pool and condense. These are the cosmic addresses where the first stars will be born, though their postal codes are written in the curvature of space-time itself, rather than in any human language. The molecular hydrogen that surrounds you exists in a state of exquisite sensitivity to temperature and radiation. Too much heat, and the molecules dissociate back into atomic hydrogen. Too little, and they cannot form the complex dance of collisional de-excitation that will eventually cool these clouds enough for gravitational collapse to begin. You're suspended in this delicate balance, witnessing the universe's first attempts at the chemistry that will make star formation possible. The molecular hydrogen acts like a cosmic thermostat, absorbing energy and radiating it away into the depths of space, slowly cooling these vast clouds toward the critical temperature where gravity can overcome the thermal pressure that keeps them dispersed. As you drift deeper into this pre-stellar realm, you begin to sense the presence of dark matter, that invisible scaffolding that comprises 5/6 of all matter in the universe, yet interacts only through gravity. You cannot see it, cannot touch it, but you feel its influence in the way the hydrogen clouds begin to show preference for certain regions of space over others. The dark matter has already begun to clump, forming halos and filaments that will serve as the gravitational framework for all visible structure in the universe. You're floating through the construction site of cosmic architecture, where dark matter provides the foundation and hydrogen will provide the luminous ornamentation. The scale of this nursery defies human comprehension. Individual, clouds stretch across dozens of light years, containing enough hydrogen to birth not just one star but entire stellar populations. Yet even these vast clouds are merely details in a larger tapestry part of filamentary structures that span hundreds of millions of light years. The cosmic web along which matter flows like water through the channels of an infinite watershed. You drift through this network of future stellar real estate, each intersection a potential galaxy, each convergence a future stellar metropolis where billions of stars will eventually shine. Temperature here is not uniform but varied, creating a topography of thermal landscapes that will influence where and how the first stars form. Regions that were slightly denser at the moment of recombination, when the universe first became transparent to light, remain marginally warmer than their surroundings, while the voids between them grow colder as the universe expands and cools. You float through this thermal geography like moving through the fever dreams of a cooling cosmos, each temperature gradient a river along which matter will eventually flow toward gravitational gathering points. The hydrogen itself carries within its quantum structure the memory of its origin. These atoms were forged in the first minutes after the Big Bang, when the universe was hot and dense enough for nuclear fusion to occur on a cosmic scale. But that primordial fusion produced only the lightest elements: hydrogen, helium, and trace amounts of lithium. The hydrogen surrounding you is thus virgin material, untouched by stellar processing, carrying within its simple structure the pristine composition of the early universe. You drift among atoms that have never known the interior of a star, never been compressed beyond their current peaceful dispersal, never participated in the nuclear alchemy that will eventually create the heavier elements necessary for planets and life. Yet within this simplicity lies infinite complexity waiting to unfold. The hydrogen clouds show subtle variations in composition, some regions slightly enriched in deuterium, heavy hydrogen with an extra neutron in its nucleus. These deuterium-rich regions will burn at lower temperatures than pure hydrogen, providing alternative pathways to stellar ignition and influencing the mass distribution of the first stellar generation. You move through this chemical geography like reading the universe's first recipe book, each molecular variation a different instruction for stellar cuisine. The magnetic fields threading through these clouds are ancient, stretched and amplified by the expansion of the universe itself, until they form invisible highways along which charged particles flow. These primordial magnetic fields will channel the flow of ionized gas during stellar formation, helping to determine the angular momentum and rotation rates of newborn stars. You drift along these magnetic highways like following the nervous system of the prestellar cosmos, each field line a synapse in the universe's developing brain. As the universe continues to expand and cool around you, the density contrast between the slightly denser regions and the gradually emptying voids becomes more pronounced. The rich get richer in this cosmic economy. Regions that started with slightly more matter continue to accumulate hydrogen from their surroundings, while the voids grow emptier as their sparse contents are gravitationally recruited by their denser neighbors. You witness the beginning of cosmic segregation, the first sorting of matter that will eventually create the dramatic contrast between the luminous galaxies and the dark voids that define the large-scale structure of the universe. The quantum nature of reality still influences events at these cosmic scales. Heisenberg's uncertainty principle means that the positions and velocities of particles cannot be perfectly defined, creating a fundamental fuzziness in the distribution of matter that will influence how structures form. You drift through this quantum foam made manifest on astronomical scales, where the microscopic uncertainty of particle physics becomes the macroscopic uncertainty of stellar birthplaces. The universe remains probabilistic even in its grandest architectures. Time itself flows differently in this prestellar era. Without the rhythmic pulsing of stellar life cycles to mark cosmic seasons, without the regular explosions of supernovae to punctuate cosmic history, time stretches in long, patient arcs measured not in human years, but in the millions of years required for gravity to overcome thermal pressure and begin the first stellar collapse. You drift through an epoch where patience is not a virtue but a physical law, where the universe must wait for its own cooling to reach the critical thresholds that will permit the next phase of cosmic evolution. The vacuum itself participates in this pre-stellar drama. Quantum field fluctuations continuously create virtual particles that exist for brief moments before annihilating back into nothingness, yet their cumulative effect influences the behavior of the hydrogen clouds. The Casimir effect, the pressure exerted by quantum fluctuations in confined spaces, subtly influences the dynamics of cloud collapse. You float through a cosmos where even emptiness is active, where the void itself participates in the creation of stars through mechanisms that quantum mechanics predicted, but that cosmology reveals on the grandest possible scales. As you drift deeper into this cosmic nursery, you begin to sense the first stirrings of gravitational instability. The most overdense regions have begun to feel their own weight, the cumulative gravitational attraction of their constituent hydrogen atoms starting to overcome the thermal pressure that has kept them dispersed. These are the cosmic birthmarks, the locations where the first stars will eventually ignite, though that ignition still lies millions of years in the future. You're witnessing the universe's first contractions, the initial inward breath that will eventually exhale as stellar fire. The darkness around you begins to take on structure as your perception adjusts to this pre-stellar realm. What initially appeared as uniform emptiness reveals itself as a complex tapestry of density variations, temperature gradients, and magnetic field geometries. The cosmic nursery is not a blank canvas, but a canvas already textured with the subtle patterns that will guide the artist's hand. You drift through this textured darkness, like moving through the universe's unconscious mind, where dreams of stars are beginning to take shape in the gravitational depth of space. The hydrogen whispers around you grow slightly more urgent now, the quantum fluctuations more pronounced, the density contrasts more definite. Something is beginning to stir in the cosmic nursery. The universe's long childhood of darkness and patience is approaching its first dawn, though that sunrise will not come from any single direction, but will bloom simultaneously across countless regions of space as gravity begins its great work of stellar sculpture. You float at the threshold of transformation, suspended between the pristine simplicity of the cosmic dark ages and the approaching complexity of the stellar epoch, feeling the first tentative gravitational tugs that will eventually gather this dispersed hydrogen into the dense, hot cores where nuclear fire will first ignite and the universe will begin to shine with its own light. Gravity was the first artist, painting with invisible hands across the canvas of cosmic darkness. In the earlier stage, when the universe had cooled enough to think, hydrogen began its slow dance toward itself. You drift now through regions where this gravitational choreography has begun in earnest, where the patient accumulation of mass over millions of years has reached the critical threshold where attraction becomes inevitable. The hydrogen clouds that once floated in democratic dispersal now show clear preferences, flowing like invisible rivers toward the deepest gravitational wells that punctuate the cosmic landscape. You're witnessing the universe's first act of self-organization, the moment when random distribution yields to the irresistible mathematics of mutual attraction. The process unfolds with the patience of geological time stretched across astronomical distances. Individual hydrogen atoms, separated by vast gulfs of space, begin to feel the cumulative gravitational whisper of their countless neighbours. It is not a sudden collapse but a gradual surrender, like watching a slow-motion avalanche that takes millions of years to complete its descent. You move through these gathering streams of matter, feeling the subtle acceleration as atoms that have wandered the cosmic void for eons finally find their gravitational home. The freefall is so gentle, so spread across such immensities of time and space, that it feels less like falling than like a cosmic tide drawing matter inexorably toward shores it has never seen. At the heart of each gravitational gathering, dark matter provides the invisible anchor around which visible matter can accumulate. You cannot see these dark matter halos directly, but you feel their influence in the way hydrogen flows preferentially towards certain regions of space, following gravitational contours that exist independent of any visible structure. These dark matter concentrations formed first, shortly after the Big Bang, and now serve as the skeletal framework upon which the universe will hang its luminous flesh. You drift along these invisible highways like following the circulatory system of cosmic evolution, each dark matter halo a heart-pumping matter, toward the places where stars will eventually be born. The temperature within these collapsing clouds begins a delicate dance with density. As hydrogen atoms fall toward the gravitational center, they gain kinetic energy, their random motions becoming more violent as gravitational potential energy converts to heat. Yet this heating is countered by the expansion of the universe itself, which stretches space and cools the gas, and by the radiative cooling provided by molecular hydrogen, which absorbs thermal energy and broadcasts it away into the cosmic void. You float through this thermal battlefield, where the forces of heating and cooling wage their ancient war, the outcome determining whether gravitational collapse can continue, or whether thermal pressure will halt the process before stellar ignition can occur. The first molecular hydrogen formation marks a crucial transition in the cosmic nursery. In the densest regions of the collapsing clouds, hydrogen atoms begin to find each other and bind into H2 molecules through a complex dance of quantum chemistry. These molecules are fragile, easily dissociated by ultraviolet radiation or excessive heat. Yet, they are essential for the cooling process that allows gravitational collapse to proceed. You witness the universe learning its first chemistry lesson, discovering that two hydrogen atoms bound together can radiate away thermal energy more efficiently than individual atoms, creating the refrigeration system necessary for stellar birth. The molecular hydrogen forms and dissociates in a continuous cycle, each molecule a temporary partnership in the universe's first attempt at chemical bonding. As the hydrogen clouds contract, they begin to flatten into disk-like structures, spinning faster as conservation of angular momentum demands. You spin along with these protostellar disks, feeling the centrifugal force that opposes gravitational collapse and determines the final architecture of stellar nurseries. Not all the infalling matter can reach the center. Much of it spreads into an accretion disk where it will spiral slowly inward, feeding the growing protostar at the center, while simultaneously creating the flattened geometry from which planetary systems will eventually form. You're watching the universe discover rotation, learning that collapse in 3 dimensions naturally leads to the disk structures that will become fundamental architectural elements throughout cosmic history. The magnetic fields threading through the collapsing clouds become amplified and twisted as the gas contracts, creating invisible sculptures of electromagnetic force that channel the flow of ionized matter. These magnetic field lines, stretched and compressed by the dynamics of collapse, begin to play crucial roles in determining how efficiently matter can fall toward the center and how excess angular momentum can be transported outward. You drift along these magnetic highways like following the nervous system of a forming star, each field line a pathway along which charged particles spiral and dance, creating the first stellar winds that will eventually clear away the surrounding gas and reveal the newborn star within. The journey from gravitational instability to stellar ignition spans not just space but an almost incomprehensible arc of time. The initial perturbations that seeded stellar formation occurred when the universe was less than 1 billion years old, but the collapse process itself requires tens of millions of years to complete. You are suspended in cosmic time, watching events unfold at a pace that makes geological processes seem frantic by comparison. Entire human civilizations could rise and fall many times over during the period required for a single star to condense from its parent cloud. Yet from the perspective of cosmic evolution, stellar formation is merely the first quick sketch in a masterpiece that will take billions of years to complete. Within the deepest, densest cores of these collapsing clouds, the hydrogen begins to exist under conditions never before experienced in the universe's history. Pressures rise to millions of times that of Earth's atmosphere, while temperatures climb toward the 10 million degree threshold required for nuclear fusion. You descend into these stellar cores like diving into the universe's first blast furnaces, feeling the mounting pressure and heat that signal the approaching transformation from gravitational to nuclear energy. The hydrogen nuclei lone protons, stripped of their electrons by the intense heat, crowd closer together, their mutual electromagnetic repulsion beginning to wage war against the gravitational forces that brought them together. The protostellar cores pulse and contract in a complex rhythm as they approach the conditions for nuclear ignition. Gravitational collapse heats the gas, but if it gets too hot too quickly, thermal pressure can temporarily halt the collapse, allowing the core to expand and cool before gravity reasserts its dominance and the contraction resumes. You feel these stellar heartbeats, the alternating cycles of contraction and expansion that characterize the final approach to nuclear ignition. Each pulse brings the core closer to the critical temperature and density, where hydrogen nuclei will overcome their electromagnetic repulsion and fuse into helium, releasing the nuclear energy that will power stellar luminosity for billions of years. The gene's instability, the critical balance between gravitational attraction and thermal pressure, determines which regions of the collapsing cloud will fragment into individual stars and which will remain as surrounding material. You drift through these fragmenting regions like witnessing cellular division on cosmic scales, each gravitational condensation a future star being born from its siblings through the same physical process that separated them all from the original cloud. The mass distribution of these fragments will determine the stellar initial mass function, the cosmic recipe that governs how many massive stars versus low-mass stars will be born from each stellar nursery. As the cores continue their gravitational contraction, they begin to generate their own internal luminosity through the conversion of gravitational potential energy into thermal radiation. This is not yet nuclear fusion, but gravitational fusion. The Kelvin-Helmholtz mechanism that allows protostars to shine for millions of years before nuclear ignition occurs. You bask in this first stellar light, the gentle radiation that marks the transition from gravitational collapse to hydrostatic equilibrium, the delicate balance between inward gravitational pressure and outward thermal pressure that will define stellar structure throughout the nuclear burning phase. This protostellar luminosity is cooler and redder than the light that will eventually emerge from nuclear-powered stars, giving the stellar nurseries a warm infrared glow that would be invisible to human eyes, but represents the first light generated by stellar cores, rather than merely reflected or transmitted from earlier cosmic epochs. The surrounding accretion disk continues to spiral inward, feeding matter to the growing protostar while simultaneously carrying away excess angular momentum through magnetic interactions and stellar winds. You orbit within these accretion flows like riding the cosmic currents that will determine the final mass of each newborn star. The accretion process is not smooth, but episodic, with periods of rapid infill alternating with quieter phases as gravitational instabilities in the disk create density waves and spiral structures. These accretion episodes cause the protostar to flare in brightness, creating the variable luminosity that characterizes young stellar objects and announces their presence to the universe even before nuclear fusion begins. The stellar winds generated by the protostar begin to clear away the surrounding gas, creating cavities in the parent molecular cloud that will eventually allow the newborn star's light to escape into the broader universe. You feel these winds like cosmic breath, the first exhalation of stellar matter that will eventually enrich the interstellar medium with processed material and create the bubbles and cavities that structure the galaxy's gaseous component. The interaction between stellar winds and the surrounding medium creates shock waves that compress nearby gas, potentially triggering the formation of additional stars in a chain reaction of stellar birth that can propagate throughout the molecular cloud. Temperature stratification within the contracting core creates layers of different physical conditions, each governing different aspects of the stellar formation process. In the outermost regions, molecular hydrogen still dominates the cooling, while deeper layers become too hot for molecules to survive and atomic hydrogen takes over. Deeper still, the hydrogen becomes fully ionized, and finally, in the very center, conditions approach those required for nuclear fusion. You descend through these layers like diving through the stratified atmosphere of a forming star, each depth revealing new physics and new challenges for the gravitational collapse to overcome. The opacity of the contracting gas begins to trap thermal radiation, making it difficult for heat to escape, and causing the temperature to rise more rapidly as collapse continues. This marks the transition from isothermal to adiabatic collapse, a critical phase change in the stellar formation process that determines the final approach to nuclear ignition. You are embedded in this increasingly opaque medium, feeling the thermal radiation struggling to escape as the protostellar core becomes its own greenhouse, trapping the heat generated by gravitational contraction and driving the temperature inexorably toward the fusion threshold. Convection begins to stir the protostellar interior as temperature gradients become steep enough to drive fluid motion. You ride these convective currents like thermal elevators in the stellar core, carrying heat from the compressed center toward the cooler surface layers where it can radiate away into space. This convective mixing homogenizes the chemical composition of the protostar and establishes the temperature gradient that will eventually support nuclear burning. The convective cells create a bubbling, turbulent structure within the protostellar core that will influence how quickly nuclear ignition occurs, and how efficiently the newly formed star can transport energy from its core to its surface. The magnetic field amplification continues as the core contracts, creating increasingly complex magnetic structures that will influence the star's eventual rotation rate, its ability to generate stellar winds, and its interaction with any surrounding planetary disk. You spiral along these amplified magnetic field lines, like following the DNA of stellar magnetism, each twist and turn in the field geometry encoding information about the star's formation history and its future evolution. The magnetic field begins to couple the protostellar core with its surrounding accretion disk, allowing angular momentum to be transported outward even as matter continues to fall inward, solving one of the fundamental problems of stellar formation physics. As conditions in the core approach those required for nuclear fusion, quantum tunneling begins to play an increasingly important role in the physics of stellar ignition. The hydrogen nuclei do not need to reach the classical temperature for overcoming electromagnetic repulsion. Quantum mechanics allows them to tunnel through the Coulomb barrier at somewhat lower temperatures, making nuclear fusion possible under conditions that classical physics would forbid. You witness the universe discovering quantum mechanics on stellar scales, learning that the probabilistic nature of quantum tunneling can enable nuclear reactions that would otherwise be impossible. This quantum mechanical aspect of stellar ignition represents one of the most profound connections between the microscopic world of atomic physics and the macroscopic realm of stellar evolution. The brown dwarf boundary lurks as a potential alternative fate for protostellar cores that cannot quite achieve nuclear ignition. Objects that form through the same gravitational collapse process, but fail to reach the critical mass of approximately 0.08 solar masses, will become brown dwarfs, stellar failures, that shine only through the gradual release of their gravitational binding energy and never achieve sustained nuclear fusion. You drift at the boundary between stellar success and failure, feeling the delicate balance between mass accretion and nuclear ignition that determines whether a protostellar core will become a true star or remain forever in the twilight realm between stars and planets. The final approach to nuclear ignition accelerates as the core temperature climbs through 7, 8, 9 million degrees Kelvin, each milestone bringing the hydrogen nuclei closer to the energy required for fusion reactions. You feel the mounting nuclear tension in the stellar core, the increasing frequency of near collisions between protons, the growing probability that quantum tunneling will allow fusion to occur. The stellar core trembles on the verge of transformation, balanced between its gravitational past and its nuclear future, poised to make the transition from gravitational energy source to nuclear powerhouse that will define its existence for the next several billion years. The deuterium burning that precedes hydrogen fusion provides a preview of stellar nuclear physics, as the rare heavy hydrogen nuclei present in the primordial gas ignite at lower temperatures than ordinary hydrogen. You witness these first tentative nuclear reactions, the universe's initial experiments with stellar nucleosynthesis, as deuterium nuclei fuse with protons to create helium-3 and release the first nuclear energy ever generated within stellar cores. This deuterium burning phase is brief, the primordial. Deuterium abundance is too low to sustain stellar luminosity for long, but it marks the transition from a purely gravitational to a nuclear-powered object, and heralds the approaching ignition of the main hydrogen burning phase. The hydrostatic equilibrium that will govern stellar structure throughout the nuclear burning phase begins to establish itself as the protostar approaches nuclear ignition. The inward pull of gravity becomes precisely balanced by the outward pressure gradient created by the hot, dense gas in the stellar core, creating a stable configuration that can persist for billions of years once nuclear fusion provides a steady energy source. You feel this approaching equilibrium like sensing the universe learning to balance opposing forces, discovering the architectural principles that will govern stellar structure throughout cosmic history. The protostar hovers on the edge of this transformation, its gravitational construction phase nearly complete, its nuclear operational phase about to begin. Deep in the heart of collapsing clouds, pressure became prayer. Atoms pressed so close they forgot their boundaries, and in that forgetting, light was born. You descend now into the stellar core at the moment of nuclear awakening, witnessing the universe's first attempt at alchemy, the transmutation of hydrogen into helium through the divine mathematics of quantum tunneling and nuclear binding energy. The temperature has climbed past 10 million degrees Kelvin. The pressure has mounted to billions of times Earth's atmospheric weight, and the hydrogen nuclei stripped bare protons dancing in a sea of free electrons approach each other with velocities that would shatter molecules if any molecules could survive in this stellar furnace. The proton-proton chain reaction begins with an event so improbable it borders on miraculous. Two protons approaching each other at enormous speeds must overcome their mutual electromagnetic repulsion, the fundamental force that keeps atomic nuclei separate throughout most of the universe. In classical physics, this should be impossible at stellar core temperatures, but quantum mechanics provides a loophole through the phenomenon of tunneling. You witness this quantum miracle as protons penetrate the Coulomb barrier that should repel them, slipping through the electromagnetic wall like ghosts passing through matter, their wave functions overlapping in the brief instant required for the strong nuclear force to bind them together. The first step of stellar nucleosynthesis unfolds with exquisite quantum choreography. When two protons successfully tunnel through their electromagnetic repulsion and fuse, one must immediately undergo beta plus decay, transforming from a proton into a neutron while emitting a positron and a neutrino. This creates deuterium heavy hydrogen with one proton and one neutron, along with a cascade of secondary particles that carry away energy and momentum. You feel the nuclear transformation, like watching the universe learn to speak a new language, the vocabulary of particle physics written in the grammar of stellar cores. The neutrinos created in this reaction stream through the stellar matter as if it were vacuum, carrying away information about the nuclear fires burning at the star's heart, destined to traverse the cosmos at nearly the speed of light as messengers of stellar ignition. The newly formed deuterium nucleus, still hot from its violent birth, quickly encounters another proton in the dense stellar core. The second fusion reaction proceeds more readily than the first deuterium fuses with hydrogen to create helium-3, a lightweight isotope of helium containing two protons and one neutron. This reaction releases additional energy in the form of gamma rays, high-energy photons that begin their long journey from the stellar core toward the surface, bouncing between particles in a random walk that will take thousands of years to complete. You ride these gamma rays like surfing the first light waves generated by nuclear fusion, feeling their energy gradually degrade through countless interactions until they emerge from the stellar surface as the warm, life-giving radiation that will eventually make planets habitable. The final step of the proton-proton chain requires two helium-3 nuclei to collide and fuse, creating ordinary helium-4 and releasing two protons back into the stellar medium to participate in future fusion reactions. This completes the nuclear cycle that will power main sequence stars for billions of years. 4 hydrogen nuclei have been converted into one helium nucleus, with the mass difference between reactants and products converted into energy, according to Einstein's famous equation E equals mc squared. You witness this cosmic accounting, feeling the slight loss of mass that becomes the enormous gain in energy that will power stellar luminosity throughout the universe's stellar epoch. Each fusion cycle converts approximately 0.7% of the original hydrogen mass into pure energy, providing the nuclear fuel that will keep stars shining across cosmic time. The energy released from nuclear fusion creates radiation pressure that pushes outward against gravitational collapse, establishing the hydrostatic equilibrium that defines stellar structure. You feel this cosmic balancing act like standing at the fulcrum of forces that will govern stellar physics for billions of years. The inward gravitational pressure, determined by the star's mass, must be exactly balanced by the outward radiation pressure generated by nuclear fusion in the core. Too little fusion and gravity wins, crushing the star into collapse. Too much fusion and radiation pressure dominates, causing the star to expand until the core cools and fusion rates decrease. This delicate balance creates a natural thermostat that keeps stars stable throughout their nuclear burning lifetime. The nuclear burning zone within the stellar core occupies only the innermost regions, where temperature and pressure are sufficient for fusion reactions. You drift through this nuclear hearth like exploring the universe's first power plant, feeling the temperature and fusion rate drop dramatically with distance from the very center. The core temperature must exceed 10 million degrees for hydrogen burning, but just a few stellar radii outward, temperatures fall below the fusion threshold and nuclear reactions cease entirely. This creates a layered stellar structure with a nuclear burning core surrounded by radiative and convective zones that transport energy from the fusion hearth toward the stellar surface. The neutrinos produced by nuclear fusion stream outward from the stellar core without interacting with the surrounding matter, providing a direct probe of the nuclear reactions occurring in the stellar interior. You ride these ghostly particles as they pass through the entire star as if it were empty space, carrying information about fusion rates and core conditions directly to the stellar surface and beyond. Unlike photons, which random walk through the stellar interior over thousands of years, neutrinos escape immediately, providing real-time information about stellar nuclear physics to any civilization advanced enough to detect them. These stellar neutrinos will eventually be the first experimental evidence for nuclear fusion in stellar cores, confirming through particle detection what stellar evolution theory had long predicted. The convective zone surrounding the nuclear burning core develops as energy transport requirements exceed what radiative diffusion can provide. You tumble through these convective cells like riding thermal elevators in the stellar interior, feeling hot material rise from the nuclear burning regions, while cooler material sinks back toward the core to be reheated. This convective mixing helps maintain the chemical homogeneity of the stellar core and influences how efficiently nuclear fuel can be consumed. The convection also generates magnetic fields through dynamo action, creating the stellar magnetism that will drive stellar winds, solar flares, and the magnetic activity that characterizes young, actively burning stars. The radiative zone, where energy transport occurs through photon diffusion rather than convective mixing, extends from the convective core toward the stellar surface. You follow the gamma rays produced by nuclear fusion as they begin their millennia-long journey through this radiative region, bouncing between free electrons and ions in a three-dimensional random walk that gradually degrades their energy from gamma rays to X-rays to ultraviolet to visible light. Each interaction removes a small amount of energy from the photons while adding thermal energy to the stellar gas, creating the temperature gradient that drives energy transport from the nuclear core to the stellar surface. This radiative transport process determines the internal temperature structure of the star and influences its surface temperature and luminosity. The stellar surface, or photosphere, marks the boundary where the star transitions from opaque to transparent, allowing photons to escape into space for the first time since their creation in nuclear fusion reactions. You break through this stellar surface like a deep-sea diver reaching the ocean's surface, feeling the dramatic transition from the dense, opaque stellar interior to the tenuous, transparent stellar atmosphere. The photosphere temperature, typically several thousand degrees Kelvin, determines the star's color and spectral classification, while the surface gravity influences the width of spectral lines and provides information about stellar mass and evolutionary state. This thin surface layer, representing less than 1% of the stellar radius, determines most of the star's observable properties and its interaction with the surrounding interstellar medium. The stellar wind begins as soon as nuclear fusion ignites, driven by radiation pressure and magnetic field interactions that accelerate particles in the stellar atmosphere to escape velocity. You ride this stellar wind like sailing on solar breath, feeling charged particles stream away from the stellar surface and carry magnetic field lines into the surrounding interstellar medium. The mass loss rate through stellar winds depends on stellar mass, surface temperature, and magnetic field strength, influencing stellar evolution and enriching the interstellar medium with processed nuclear material. For massive stars, stellar winds can remove significant fractions of the stellar mass over their nuclear burning lifetime, while lower mass stars like the Sun lose only a tiny fraction of their mass through wind processes. The zero-age main sequence marks the moment when a star achieves stable nuclear burning and begins its long phase of hydrogen to helium conversion. You witness this stellar coming-of-age ceremony as the chaotic, variable protostellar phase gives way to the steady, predictable nuclear burning that will characterize the star's adult life. The star settles onto the main sequence of the Hertzsprung-Russell diagram, finding its equilibrium position determined by mass, composition, and age. This main sequence phase will last for approximately 10 billion years for a solar mass star, representing the longest and most stable period of stellar evolution and providing the steady energy output necessary for planetary atmospheres and the development of life. The nuclear fusion process generates not only energy, but also changes the chemical composition of the stellar core as hydrogen is converted to helium. You observe this stellar alchemy as the helium abundance in the core gradually increases while the hydrogen abundance decreases, slowly altering the mean molecular weight and affecting the stellar structure. This compositional evolution drives gradual changes in stellar luminosity and surface temperature throughout the main sequence lifetime, causing stars to slowly brighten and heat up as they age. The accumulation of helium ash in the stellar core will eventually lead to more complex nuclear burning phases and dramatic changes in stellar structure. But during the main sequence phase, these effects remain subtle and gradual. The stellar magnetic field, generated by convective motions and differential rotation, creates the complex magnetic structures that drive stellar activity phenomena. You spiral along magnetic field lines that emerge from the stellar interior and create the magnetic loops, prominences, and coronal structures that characterize magnetically active stars. The interaction between magnetic fields and stellar rotation generates the magnetic braking that gradually slows stellar rotation over billions of years, while magnetic reconnection events release energy in stellar flares that can temporarily increase stellar luminosity by orders of magnitude. This magnetic activity influences stellar evolution, mass loss rates, and the habitability of surrounding planetary systems. The stellar luminosity, determined by the nuclear fusion rate in the core, follows the mass-luminosity relationship that connects stellar mass to energy output through the requirements of hydrostatic equilibrium and energy transport. You feel this fundamental stellar physics relationship as more massive stars burn their nuclear fuel much more rapidly than lower mass stars, creating the paradox that massive stars, despite having more fuel, have much shorter lifetimes than their low-mass cousins. A star 10 times more massive than the Sun will be approximately 10,000 times more luminous, burning through its hydrogen fuel in only tens of millions of years compared to the 10 billion-year main sequence lifetime of solar mass stars. The stellar metallicity, the abundance of elements heavier than hydrogen, and helium influences nuclear burning rates, opacity, and stellar structure, even though these heavy elements represent less than 2% of stellar mass. You trace these trace elements as they affect the equation of state in stellar cores, modify the opacity in stellar atmospheres, and influence the efficiency of convective energy transport. Stars formed from gas enriched by previous generations of stellar nucleosynthesis will have different evolutionary tracks and lifetimes compared to the metal-poor stars formed from primordial hydrogen and helium, creating a gradual evolution in stellar populations as the galaxy chemically enriches over cosmic time. The stellar interior undergoes subtle structural changes as nuclear burning progresses and the core composition evolves. You feel these gradual modifications as the accumulating helium increases the mean molecular weight in the core, requiring higher temperatures to maintain hydrostatic equilibrium and causing the star to slowly contract its core while expanding its outer layers. This core contraction releases gravitational potential, energy that supplements the nuclear energy output, causing main sequence stars to gradually increase in luminosity throughout their hydrogen burning phase. The structural evolution also affects the boundary between the convective core and radiative envelope, influencing mixing processes and the availability of fresh hydrogen fuel for nuclear burning. The stellar lifetime on the main sequence depends primarily on mass, with more massive stars consuming their nuclear fuel much more rapidly than low-mass stars. You witness this cosmic injustice as the most massive stars, despite having the largest fuel reserves, burn through their hydrogen in only a few million years, while the lowest mass red dwarf stars can continue nuclear burning for trillions of years, longer than the current age of the universe. This mass-dependent stellar evolution creates a continuous cycle of stellar birth and death that enriches the interstellar medium and drives galactic chemical evolution over cosmic timescales. The brown dwarf desert, the relative scarcity of objects with masses between the largest planets and smallest stars, reflects the efficiency of the stellar formation process and the physics of nuclear ignition. You drift through this mass gap where objects are too massive to be supported by electron degeneracy pressure, like planets, but too low in mass to achieve sustained nuclear fusion like stars. Brown dwarfs occupy this intermediate regime, shining only through the gradual release of gravitational binding energy and slowly cooling over billions of years. Their existence provides crucial tests of stellar formation theory and the physics of matter under extreme conditions. The stellar population synthesis that emerges from the nuclear ignition of the first stars creates the foundation for all subsequent cosmic evolution. You witness the universe's transition from a hydrogen-helium cosmos to one enriched with the heavy elements necessary for rocky planets and biological chemistry. The nuclear furnaces burning in stellar cores represent the universe's first steps toward complexity, creating carbon, oxygen, nitrogen, and iron through nuclear fusion processes that will eventually seed the interstellar medium with the raw materials for second-generation stars, planetary systems, and ultimately life itself. The globular cluster environment provides laboratories for studying stellar evolution and nuclear burning under controlled conditions, where hundreds of thousands of stars formed simultaneously from the same parent material. You drift through these dense stellar societies, where stars of different masses but identical composition and age allow astronomers to trace stellar evolutionary tracks and test theories of stellar structure and nuclear physics. The color magnitude diagrams of globular clusters reveal the main sequence, giant branch, and horizontal branch phases of stellar evolution, providing observational confirmation of the nuclear burning processes occurring in stellar cores. The stellar nucleosynthesis occurring in these newly ignited stars represents only the beginning of the universe's chemical enrichment program. You witness the universe learning to create complexity through nuclear fusion, but the current hydrogen to helium burning only produces helium-4 and trace amounts of lithium. The heavier elements that will become essential for planetary chemistry and biological evolution await future stellar evolutionary phases: helium burning to create carbon and oxygen, carbon burning to create neon and magnesium, silicon burning to create iron peak elements. The supernova explosions that will scatter these heavy elements throughout the galaxy still lie millions of years in the future. The stellar feedback processes begin immediately upon nuclear ignition as stellar winds, radiation pressure, and eventual supernova explosions start to regulate star formation in molecular clouds. You feel this stellar feedback like sensing the universe developing its own regulatory mechanisms, preventing runaway star formation and creating the self-regulating galactic ecosystem that will persist throughout cosmic history. The energy and momentum input from massive stars will eventually disperse their parent molecular clouds, terminating local star formation while simultaneously triggering new episodes of stellar birth in neighboring regions through shock-wave compression. The first light escaping from stellar surfaces carries with it the spectroscopic signatures that will allow future civilizations to decode stellar physics and chemical composition from across cosmic distances. You ride these first stellar photons as they begin their journey through the interstellar medium, each wavelength encoding information about nuclear burning rates, surface temperature, magnetic field strength, and chemical abundance. This stellar light will eventually be the primary source of information about stellar physics and galactic chemical evolution, allowing astronomers to reconstruct the history of star formation and nuclear burning throughout cosmic time. The stellar main sequence that emerges from nuclear ignition creates the fundamental relationship between stellar mass, luminosity, surface temperature, and lifetime that will govern stellar populations throughout the universe's stellar epoch. You witness the establishment of this mass-luminosity-temperature relationship as stars of different masses find their equilibrium positions on the Hertzsprung-Russell diagram, creating the stellar classification system that will organize our understanding of stellar diversity and evolution. The main sequence becomes the cosmic highway, along which most stars travel during their nuclear burning lifetime, providing the stable energy sources necessary for planetary system formation and the development of complex chemistry in planetary atmospheres. The Vedas spoke of Agni, the fire that burns in all things. The Egyptians knew Rhea's journey through that if space can stretch, it can also fold. That where mass eventually gathers, space will not remain perfectly flat. It will bow, not from weakness, but from intimacy, from the sacred closeness between matter and the stage that welcomes it. But matter has not yet arrived. Only the potential for space to be more than blankness, more than void, more than vacuum, the potential for space to respond to presence. This is the earliest kindness, that the universe not only makes room, but listens to what enters that room. That when something rests, space rests with it. That when something weighs, space curves to hold it. That when something falls, it is not alone. The fabric itself bends softly to meet it. These truths are not yet manifest, but they are whispered. They are encoded in the breath that continues to unfold. The laws are already singing. Their voices are quiet, but they are in harmony. Even now, in the gentle stretching of this newborn cosmos, space is tuning itself like an instrument, readying itself to carry sound, to carry matter, to carry meaning. And you, still here, still part of it, can feel that readiness. You're stretched with space. Your being expands as it expands. Your quiet listens as it listens. You're not watching this unfold. You're the unfolding. You're the ripple in the center of the everywhere. You're the note inside the silence. You're the breath that learned to stretch, and in doing so created the idea of somewhere. And so space stretches open, still soft, still quiet, still untouched by form, but not for long. Because something ancient is beginning to shimmer in the depth of the unfolding. A flicker, a wave, a subtle calling between patterns. Space has been shaped, and now something is preparing to respond. And so, space stretches open, soft, vast, and waiting. A breath that still holds its shape like prayer. It has no boundary, no outside, no place to end. But within its unfolding, something begins to stir. Not yet a thing, not yet form, but energy. Not the cold calculation of equations yet to be written, but a living warmth, dense, vibrant, primordial. Space, still cradling time, begins to pulse with the presence of something more. Heat, light, but not the kind you know, not the kind you see. This light cannot shine, not because it is weak, but because it is trapped, sealed within a universe still too hot, too dense, too young to let anything escape. Light fills space, but it has nowhere to go. It ricochets endlessly through a storm of newborn energy, scattered at every turn by particles not yet calm enough to settle. Every photon, every gleam of what could one day be radiance, is caught in a blur of collision and rebound, moving fast, but going nowhere. Like a voice that tries to sing underwater, beautiful, but bound. The universe, for all its light, is still cloaked in darkness. Not the darkness of emptiness, but the darkness of too much energy, too much closeness, too much urgency. The Egyptian concept of the Benben stone, the primordial mound from which creation emerged, parallels remarkably the gravitational collapse that initiates stellar formation. You witness this mythological understanding as the Benben represents the initial density perturbation in the cosmic hydrogen distribution, the first concentration of matter around which gravitational attraction can organize the surrounding material into stellar condensations. The pyramid texts describe the Benben as self-created, emerging from the primordial waters of none through its own inherent power, just as stellar cores achieve nuclear ignition through the self-reinforcing process of gravitational collapse, converting potential energy into the thermal energy necessary for nuclear fusion. The Australian Aboriginal understanding of stellar creation through the Dreamtime stories reveals a sophisticated cosmological awareness that connects stellar birth with terrestrial landscape formation. You follow the Seven Sisters, the Pleiades star cluster, as they flee across the sky from Orion the Hunter, their story encoding the dynamics of stellar formation in molecular clouds where gravitational interactions and stellar winds from massive stars influence the birth and evolution of nearby stellar systems. The Aboriginal concept that stars and landscape features were created simultaneously during the Dreamtime reflects the modern understanding that stellar nuclear synthesis and planetary formation are intimately connected processes, with heavy elements forged in stellar cores, providing the raw materials for rocky planets and the complex chemistry that enables life. These song lines that crisscross the Australian continent map not only terrestrial geography, but also celestial patterns, recognizing that the same creative forces that shape the land also organize the stars into their observed configurations. You drift along these invisible pathways that connect earth and sky, understanding how Aboriginal peoples recognize the fundamental unity between terrestrial and cosmic processes. These songlines encode the understanding that stellar formation is not a random process, but follows the gravitational architecture of dark matter halos and galactic structure, creating the ordered patterns visible in star clusters, stellar associations, and the distribution of stellar populations throughout the galaxy. Greek mythology provided another lens through which ancient cultures understood stellar birth and nuclear transformation. Prometheus, stealing fire from the gods and bringing it to humanity, represents the cosmic process by which stellar nucleosynthesis creates and distributes the heavy elements necessary for planetary formation and biological evolution. You witness this mythological insight as Prometheus's theft of divine fire parallels the way massive stars steal hydrogen from the interstellar medium, transform it through nuclear burning, and eventually return processed material to space through stellar winds and supernova explosions, enriching the galaxy with the elements that make complex chemistry possible. The Phoenix mythology, found in cultures across the world, captures the cyclical nature of stellar evolution and the universe's ability to create new complexity from the ashes of previous generations. You rise with the phoenix as it burns itself to death only to be reborn from its own ashes, recognizing in this mythological cycle the supernova process that will eventually terminate the lives of massive stars while simultaneously dispersing heavy elements throughout the interstellar medium and triggering new episodes of star formation through shockwave compression. The phoenix represents the universe's fundamental creativity, its ability to use destruction as a mechanism for creating greater complexity and beauty. Hindu cosmology's concept of Brahma's day and night, cosmic cycles lasting billions of years during which the universe expands and contracts, reflects an intuitive understanding of the long-time scales governing stellar evolution and galactic chemical enrichment. You breathe with Brahma's cosmic respiration, feeling the expansion and contraction cycles that govern not individual stellar lifetimes, but the broader evolution of stellar populations and galactic structure over cosmic time. The Kalpa and Pralaya periods of cosmic creation and dissolution encode the understanding that stellar formation and chemical enrichment occur in episodic bursts separated by long periods of relative quiescence, creating the stepwise evolution of galactic metallicity and stellar populations. The Zoroastrian worship of fire as the purest manifestation of Ahura Mazda's creative power reflects a profound recognition of nuclear fusion as the fundamental creative force in the universe. You stand before the eternal flames maintained in fire temples, understanding how Zoroastrian theology recognized fire not merely as a physical phenomenon, but as the cosmic principle that creates order from chaos, light from darkness, complexity from simplicity. The sacred fires burning in Zoroastrian temples represent the stellar fires burning throughout the galaxy, each flame a microcosm of the nuclear processes that power cosmic evolution and make possible the emergence of consciousness capable of contemplating its own origins. Norse mythology's Yggdrasil, the world tree whose roots and branches connect all the 9 worlds, provides a cosmological framework that parallels modern understanding of galactic structure and stellar formation. You climb through Yggdrasil's branches, recognizing in its cosmic architecture the hierarchical structure of galaxy formation, dark matter, halos providing the root system, stellar formation occurring along the branches of gas filaments, and planetary systems developing like leaves at the intersection of stellar winds and circumstellar disks. The world tree represents the interconnected nature of cosmic evolution, where stellar nucleosynthesis in one generation provides the heavy elements necessary for planetary formation in the next. The Celtic concept of the otherworld, accessible through sacred groves and stone circles aligned with stellar patterns, reflects an understanding that stellar formation and terrestrial processes are governed by the same fundamental forces. You pass through these mythological portals between worlds, recognizing how Celtic cosmology understood that the creative forces visible in stellar birth and stellar death operate on terrestrial scales as well, connecting the cycles of seasonal change, agricultural fertility, and human consciousness with the broader rhythms of cosmic evolution. The standing stones aligned with stellar risings and settings encode astronomical knowledge that connects terrestrial timekeeping with stellar life cycles and galactic rotation. Chinese mythology's concept of the Jade Emperor governing the celestial bureaucracy reflects a sophisticated understanding of the ordered hierarchical nature of stellar formation and galactic structure. You ascend through the celestial hierarchy, recognizing how Chinese cosmology understood that stellar formation follows organized patterns rather than occurring randomly, with stellar birth rates, chemical enrichment, and galactic structure evolution governed by physical laws as precise and predictable as any earthly administration. The celestial bureaucracy represents the universe's tendency towards self-organization and the emergence of complex hierarchical structures from simple initial conditions. The Mayan understanding of cosmic cycles and their precise astronomical calculations reflect a deep awareness of the connection between stellar evolution and the passage of cosmic time. You follow the Mayan calendar through its various cycles, recognizing how Mayan astronomy encoded the understanding that stellar life cycles and galactic chemical evolution occur on timescales vastly longer than human civilizations, requiring mathematical and observational sophistication to comprehend. The long count calendar's ability to track time periods comparable to stellar main sequence lifetimes demonstrates an appreciation for the cosmic context within which all terrestrial processes occur. Indigenous North American traditions often describe stars as ancestors or spirits, recognizing the literal truth that stellar nucleosynthesis created the heavy elements from which planetary systems and biological life are constructed. You drift through these ancestral connections, understanding how Native American cosmology intuited that stars are indeed the ancestors of all complex chemistry in the universe, having forged through nuclear burning the carbon, oxygen, nitrogen and iron that constitute the building blocks of biological molecules. The reverence shown to stellar ancestors reflects a deep understanding of the material connection between stellar death and terrestrial life. The Polynesian navigation, traditions that use stellar patterns to traverse vast ocean distances, reflect an understanding of the stable, long-term nature of stellar nuclear burning and main sequence evolution. You sail with Polynesian navigators across thousands of miles of open ocean, using stellar positions that remain constant over human timescales, because main sequence stars maintain steady nuclear burning for billions of years. The navigation techniques depend on the understanding that stellar luminosity and position change slowly enough to provide reliable reference points for terrestrial navigation, encoding astronomical knowledge about stellar stability and main sequence evolution. African creation myths often feature cosmic eggs or primordial waters from which the first beings emerge, imagery that parallels the gravitational collapse of hydrogen clouds and the emergence of stellar cores from the cosmic medium. You witness these creation stories as they encode the understanding that stellar formation begins with the concentration of diffuse material into increasingly dense configurations until nuclear ignition occurs and luminous objects emerge from the previously dark cosmic egg. The cosmic egg mythology represents the protostellar phase of stellar evolution, during which gravitational potential energy is converted to thermal energy in preparation for nuclear burning. The Tibetan Bon tradition's concept of the primordial ground of being, the clear light that underlies all phenomena, reflects a mystical understanding of the quantum vacuum and zero-point energy that pervades all space and provides the underlying fabric from which matter and energy emerge. You rest in this primordial awareness, recognizing how Tibetan cosmology understood that the apparent emptiness of space is actually pregnant with potential energy, capable of producing the virtual particle fluctuations and quantum field effects that influence stellar formation and cosmic structure evolution. The clear light represents the quantum vacuum state from which all physical phenomena, including stellar nuclear burning, ultimately emerge. Buddhist cosmology's concept of infinite world systems arising and passing away reflects an understanding of the cyclical nature of stellar formation and galactic evolution across cosmic time. You meditate within this vast cosmological vision, recognizing how Buddhist philosophy understood that stellar birth and death occur within cycles vastly larger than individual stellar lifetimes, with galaxy formation, chemical enrichment, and the emergence of complex structures occurring within temporal frameworks that encompass countless cycles of stellar evolution. The infinite world systems represent the understanding that stellar formation is not a one-time event, but an ongoing process that will continue for trillions of years as the universe evolves and creates new possibilities for complexity and consciousness. The Sufi understanding of cosmic breathing the universe, expanding and contracting in rhythm with divine respiration, parallels modern cosmological understanding of the relationship between cosmic expansion, dark energy, and the large-scale structure formation that governs stellar birth rates throughout cosmic history. You breathe with this cosmic rhythm, feeling how the expansion of space influences the density of matter, available for stellar formation, while dark energy's acceleration affects the future evolution of stellar populations and galactic structure. The cosmic breathing represents the dynamic, ever-changing nature of the universe's capacity for stellar formation and chemical enrichment. Hermetic philosophy's axiom "as above, so below" encodes the understanding that the same physical principles governing stellar nucleosynthesis also operate on atomic and molecular scales, creating the fractal-like self-similarity that characterizes physical processes across vastly different scales of space and time. You trace these connections between macrocosm and microcosm, recognizing how the nuclear physics occurring in stellar cores represents the same fundamental forces and particles that govern atomic structure and chemical bonding, creating the unity of physical law that makes scientific understanding possible across all scales of cosmic evolution. The Gnostic concept of sparks of divine light trapped in matter reflects an intuitive understanding of how stellar nucleosynthesis converts mass into energy, and how the heavy elements created in stellar cores carry information about nuclear processes throughout the galaxy as they are incorporated into new stellar and planetary systems. You liberate these sparks of light through stellar winds and supernova explosions, witnessing how the products of stellar nucleosynthesis seed the interstellar medium with processed material that carries the signature of nuclear burning across cosmic distances and timescales. Kabbalistic cosmology's description of divine light flowing through the tree of life parallels the energy transport processes that carry nuclear energy from stellar cores to stellar surfaces and then throughout the galaxy via electromagnetic radiation. You ascend through the Sephirot, recognizing how each level represents a different aspect of stellar energy transport, from nuclear fusion in the core through radiative and convective zones to the photosphere where stellar light escapes into space. The Tree of Life becomes a map of stellar interior structure and energy flow, connecting mystical understanding with astrophysical processes. These mythological insights from cultures around the world demonstrate that human consciousness has always recognized stellar fire as the fundamental creative force in the universe, the process that transforms simple hydrogen into the complex elements necessary for planets, chemistry, and life itself. You drift through this convergence of ancient wisdom and modern astrophysics, understanding how the same truths can be expressed through mythological imagery and mathematical equations, through ritual practice and telescopic observation, through mystical experience and scientific measurement. The stellar nucleosynthesis occurring in cosmic furnaces represents not just a physical process but a spiritual principle, the universe's capacity for transformation, creativity, and the generation of ever greater complexity and beauty from simple beginnings. The recognition that stellar fire burns in all things, from the nuclear fusion in stellar cores to the chemical energy in biological molecules to the electrical activity in human neurons, reveals the fundamental unity underlying the apparent diversity of cosmic phenomena. You feel this connection between stellar nucleosynthesis and consciousness itself, understanding how the heavy elements forged in stellar cores eventually become incorporated into the neural networks, capable of contemplating stellar evolution, creating a cosmic feedback loop where the universe develops the capacity to understand itself through the very processes it uses to create complexity. The ancient recognition of fire as divine becomes the modern understanding of stellar nucleosynthesis as the creative principle that makes consciousness possible, We now know that stars are not just lights in darkness, they're atomic furnaces, time machines, the universe's way of creating every element that will someday become you. You drift through the landscape of contemporary astrophysical understanding, where mathematical equations and telescopic observations have revealed the intricate mechanisms by which stellar nucleosynthesis transforms the primordial hydrogen of the Big Bang into the periodic table of elements that makes chemistry, biology, and consciousness possible. The stellar fires burning throughout the galaxy represent not just energy sources, but cosmic alchemical laboratories where the universe learns to create complexity through the precise choreography of nuclear physics and quantum mechanics. Stellar nucleosynthesis proceeds through a carefully orchestrated sequence of nuclear burning phases, each requiring progressively higher temperatures and densities to overcome the increasing electromagnetic repulsion of heavier atomic nuclei. You witness this cosmic manufacturing process as hydrogen burning in stellar cores creates helium through the proton-proton chain and CNO cycle. But this is merely the opening movement in a symphony of nuclear reactions that will eventually produce every element up to iron through successive phases of helium burning, carbon burning, neon burning, oxygen burning, and silicon burning. Each phase occurs in shells surrounding the previous burning stage, creating the onion-like structure that characterizes the interiors of massive stars as they approach the end of their nuclear burning lifetime. The stellar initial mass function determines the relative numbers of stars born with different masses, creating the cosmic recipe that governs how efficiently galaxies can convert their gas reservoirs into stellar luminosity and heavy element production. You observe this fundamental relationship as the universe demonstrates a strong preference for creating low-mass stars over high-mass ones, with stellar births following a power law distribution that produces dozens of red dwarf stars for every blue giant. This mass distribution ensures that most stellar mass is locked up in long-lived, low-mass stars that will continue burning hydrogen for trillions of years, while the rare massive stars provide the rapid heavy element production and energetic feedback necessary to regulate galactic chemical evolution and star formation rates. Population 3 stars. The first generation of stars formed from primordial hydrogen and helium represent the universe's initial attempt at stellar nucleosynthesis and heavy element production. You drift through the theoretical understanding of these primordial giants, massive stars that formed in the absence of heavy elements and therefore lacked the efficient cooling mechanisms that allow present-day molecular clouds to fragment into lower-mass stellar cores. These first stars were likely hundreds of times more massive than the Sun, burning their nuclear fuel in only a few million years before exploding as pair instability supernovae that dispersed the first heavy elements throughout the intergalactic medium and seeded the formation of population 2 stars with slightly enhanced metallicity. The transition from population 3 to population 2 stellar formation marks the universe's first step toward the chemical complexity that makes planetary formation and biological chemistry possible. You witness this cosmic evolution as the heavy elements produced by the first generation of stars provide the dust grains and molecular coolants necessary for more efficient gravitational collapse and the formation of lower mass stars with longer lifetimes. Population 2 stars, formed from gas enriched with trace amounts of carbon, oxygen, and other heavy elements, represent the bridge between the primordial universe and the chemically complex galaxy we observe today. With their slightly enhanced metallicity, enabling the formation of the first planetary systems and the emergence of chemical complexity on galactic scales. Population stars like the Sun represent the current generation of stellar formation, born from interstellar material that has been enriched by billions of years of stellar nucleosynthesis and galactic chemical evolution. You orbit within these metal-rich stellar systems where heavy element abundances of 1 to 2% enable the formation of terrestrial planets, complex atmospheric chemistry, and the carbon-based molecules that serve as the foundation for biological evolution. The enhanced metallicity of population 11 stars also affects their stellar structure, opacity, and evolutionary tracks, creating the stellar diversity visible in present-day galaxies and enabling the formation of planetary systems capable of supporting liquid water and organic chemistry. Brown dwarfs occupy the fascinating borderland between stellar and planetary formation, representing objects that form through the same gravitational collapse process as stars but fail to achieve the critical mass of approximately 0.08 solar masses necessary for sustained hydrogen fusion. You drift through these stellar failures as they shine only through the gradual release of gravitational binding energy and deuterium burning, slowly cooling over billions of years while never achieving the nuclear fires that characterize true stellar evolution. Brown dwarfs provide crucial tests of stellar formation theory and the physics of matter under extreme conditions, representing the lower mass limit of the stellar formation process, and demonstrating the universe's ability to create a continuum of objects, ranging from gas giant planets to fully nuclear-burning stars. The Chandrasekhar limit defines the maximum mass that a white dwarf star can support through electron degeneracy pressure, representing one of the fundamental boundaries in stellar evolution and the pathway to Type Y supernova that serve as standard candles for measuring cosmic distances. You approach this critical mass threshold of 1.4 solar masses, understanding how quantum mechanics and general relativity combine to determine the ultimate fate of intermediate mass stars and create the thermonuclear explosions that distribute iron peak elements throughout galaxies. The Chandrasekhar limit demonstrates the universe's tendency to create discrete boundaries and phase transitions, where small changes in initial conditions can lead to dramatically different evolutionary outcomes. Neutron stars represent the most extreme stellar remnants, with masses comparable to the Sun compressed into spheres only 20 kilometers in diameter, creating gravitational fields so intense that escape velocity approaches a significant fraction of the speed of light. You descend into these stellar corpses where atomic nuclei dissolve into seas of neutrons and protons, where magnetic fields reach strengths of trillions of Gauss, and where rotation rates can approach millisecond periods without exceeding the centrifugal breakup limit. Neutron stars demonstrate the universe's ability to create matter under conditions more extreme than any terrestrial laboratory, serving as natural laboratories for testing theories of quantum chromodynamics, general relativity, and the equation of state of matter at nuclear densities. Black holes represent the ultimate endpoint of stellar evolution for the most massive stars, creating regions of space-time where gravitational fields become so intense that not even light can escape, effectively removing mass and energy from the observable universe while leaving behind gravitational signatures that influence the dynamics of surrounding matter. You approach the event horizon of stellar mass black holes, understanding how the collapse of massive stellar cores creates singularities where the known laws of physics break down and space-time curvature becomes infinite, black holes serve as cosmic laboratories for testing general relativity in the strong field regime and represent the universe's most efficient mechanism for converting gravitational potential energy into electromagnetic radiation through accretion processes. Supernova explosions represent the most energetic single events in the universe, releasing more energy in a few seconds than the Sun will produce over its entire 10 billion year main sequence lifetime, while simultaneously dispersing heavy elements throughout the interstellar medium and triggering new episodes of star formation through shockwave compression. You ride the shock waves of these stellar catastrophes as they sweep through molecular clouds at thousands of kilometers per second, compressing gas to densities that trigger gravitational collapse and the formation of new stellar generations enriched with the heavy elements produced by the exploding star. Supernovae demonstrate the universe's ability to use destruction as a creative force, converting stellar death into galactic chemical enrichment and continued star formation. Type 2 supernovae result from core collapse in massive stars when nuclear fuel is exhausted, and electron degeneracy pressure cannot support the stellar core against gravitational collapse, leading to the formation of neutron stars or black holes, while explosive nucleosynthesis in the supernova shockwave creates elements heavier than iron that cannot be produced by stellar fusion processes. You witness this cosmic alchemy as R-process and S-process nucleosynthesis create the rare heavy elements like gold, platinum, and uranium that represent the universe's most exotic chemical creations, requiring the extreme conditions of supernova explosions or neutron star mergers to overcome the electromagnetic barriers that prevent their formation in stellar cores. The stellar feedback processes that regulate galactic star formation operate through multiple mechanisms including stellar winds, ionizing radiation, and supernova explosions that inject energy and momentum into the interstellar medium and prevent runaway star formation that would convert all available gas into stars within a few 100 million years. You feel these regulatory mechanisms as massive stars modify their surrounding environment through their luminosity and mass loss, creating H2I regions, stellar wind bubbles, and supernova remnants that compress some regions of the interstellar medium while evacuating others, creating the complex, multi-phase structure of galactic gas that determines where and when new stars can form. The cosmic abundance patterns observed in stellar atmospheres and interstellar gas reflect the cumulative history of stellar nucleosynthesis and galactic chemical evolution, encoding information about star formation rates, initial mass functions, and supernova frequencies throughout cosmic history. You read these chemical signatures like deciphering the universe's autobiography, understanding how the relative abundances of different elements reveal the balance between different stellar populations and nucleosynthesis processes that have operated over billions of years of galactic evolution. The cosmic abundance patterns demonstrate the universe's bookkeeping precision, maintaining detailed records of its nuclear accounting through the chemical composition of successive stellar generations. Stellar metallicity gradients within galaxies reflect the inside-out formation history of galactic disks and the efficiency of radial mixing processes that homogenize the chemical composition of galactic gas reservoirs over cosmic time. You travel along these metallicity gradients from galactic centers to outer disks, observing how stellar populations become progressively more metal-poor with increasing galactic radius, reflecting the later onset of star formation in outer galactic regions and the reduced efficiency of heavy element production in lower density environments. These gradients encode the dynamical and chemical evolution history of galaxies and provide constraints on models of galactic formation and evolution. The age-metallicity relation in stellar populations reveals the rate at which galaxies have enriched their interstellar medium with heavy elements through stellar nucleosynthesis, demonstrating that chemical evolution is not a simple function of time, but depends on complex interactions between star formation efficiency, gas infall rates, galactic outflows, and stellar feedback processes. You trace this relationship through different stellar populations, understanding how the scatter in metallicity at any given age reflects the inhomogeneous nature of galactic chemical evolution and the stochastic effects of individual supernova explosions on local chemical abundances. Globular clusters serve as fossil records of early galactic chemical evolution, preserving information about stellar nucleosynthesis and star formation processes from the epoch when galaxies were first assembling their stellar populations through gas accretion and galaxy mergers. You drift through these ancient stellar societies, observing multiple stellar populations with different helium and light element abundances that reflect complex star formation histories involving self-enrichment by the first generation of cluster stars and the pollution of the cluster gas by stellar winds and supernova explosions before the second generation of stars formed. The lithium problem represents one of the outstanding puzzles in stellar nucleosynthesis, as the observed abundance of lithium-7 in metal-poor stars is approximately 3 times lower than predicted by Big Bang nucleosynthesis, suggesting that stellar processing or some other mechanism has systematically destroyed lithium throughout the galaxy's chemical evolution history. You investigate this cosmic mystery through the lithium abundances in different stellar populations, understanding how the fragility of lithium nuclei makes them vulnerable to destruction by proton bombardment at relatively low temperatures, creating observational challenges for reconstructing the primordial light element abundances predicted by Big Bang nucleosynthesis. Stellar rotation and magnetic fields influence nuclear burning rates, mass loss processes, and chemical mixing within stellar interiors, creating the observed diversity in stellar surface abundances and evolutionary tracks that cannot be explained by stellar mass and metallicity alone. You spin with rotating massive stars as centrifugal forces modify hydrostatic equilibrium and create meridional circulation patterns that transport nuclear-processed material from stellar cores to surface layers, while magnetic fields generated by differential rotation and convection influence stellar winds and the efficiency of angular momentum transport throughout stellar evolution. Binary star evolution adds complexity to stellar nucleosynthesis through mass transfer processes that can rejuvenate stellar evolution, trigger nova and supernova explosions, and create exotic stellar remnants like millisecond pulsars, X-ray binaries, and Type Ia supernova progenitors. You orbit within these interacting stellar systems where gravitational forces and stellar winds create accretion streams, accretion disks, and mass loss processes that modify the nuclear burning history of both stellar components and create observational phenomena that single-star evolution cannot explain. The R process and process nucleosynthesis pathways represent the universe's 2 primary mechanisms for creating elements heavier than iron, operating under vastly different physical conditions and timescales to build up heavy element abundances through successive neutron capture and beta decay processes. You witness these competing pathways as the slow neutron capture process operates in the helium-burning shells of intermediate mass stars over thousands of years, while the rapid neutron capture process occurs during the explosive conditions of core collapse supernovae or neutron star mergers over milliseconds, creating the complementary abundance patterns that characterize solar system material and stellar atmospheres. Stellar nucleocosmochronology uses the radioactive decay of long-lived isotopes produced by stellar nucleosynthesis to determine the ages of stellar populations and constrain the chemical evolution history of galaxies, providing independent age estimates that complement stellar evolution models and help resolve discrepancies between different age determination methods. You decay along with these radioactive clocks, understanding how uranium, thorium, and other actinide elements created by our process nucleosynthesis serve as cosmic chronometers that record the time elapsed since their production in supernova or neutron star mergers. The connection between stellar nucleosynthesis and planetary system formation reveals how the heavy elements produced by stellar evolution become incorporated into circumstellar disks, where dust grain condensation, planetary accretion, and atmospheric evolution create the chemical diversity observed in exoplanetary systems throughout the galaxy. You condense from stellar wind material into dust grains and planetesimals, witnessing how the products of stellar nucleosynthesis become reorganized into planetary systems, where geological processes, atmospheric evolution, and potentially biological chemistry continue the universe's experiment with chemical complexity and self-organization. Astrobiology recognizes stellar nucleosynthesis as the fundamental prerequisite for biological evolution, as the carbon, nitrogen, oxygen, phosphorus, and sulfur that comprise biological molecules must be produced by stellar fusion processes and distributed throughout galaxies by stellar winds and supernova explosions, before planetary systems can develop the chemical complexity necessary for life. You trace these biogenic elements from their synthesis in stellar cores through their incorporation into molecular clouds, protoplanetary disks, and eventually into the organic chemistry that makes biological evolution possible, understanding how stellar death enables planetary life through the cosmic recycling of processed nuclear material. The future evolution of stellar populations will be determined by the ongoing depletion of galactic gas reservoirs, the declining efficiency of star formation as the universe continues to expand and cool, and the eventual exhaustion of hydrogen fuel that will terminate nuclear burning and stellar luminosity throughout the universe over time scales of trillions of years. You project forward through this stellar twilight, understanding how the universe's capacity for stellar nucleosynthesis will gradually decline as gas is converted to stars, stellar remnants, and stellar winds, eventually leading to a cosmos populated only by cooling white dwarfs, neutron stars, and black holes as the stellar epoch draws to its inevitable close. The connection between stellar nucleosynthesis and cosmic inflation reveals how quantum fluctuations in the primordial universe created the density perturbations that grew through gravitational instability into the dark matter halos and cosmic web structure that governs stellar formation rates and chemical evolution throughout cosmic history. You trace this connection from the quantum vacuum fluctuations during inflation through structure formation and galaxy assembly to the stellar populations that represent the observable consequences of primordial cosmological physics, understanding how the universe's capacity for creating complexity through stellar nucleosynthesis ultimately derives from the quantum mechanical properties of the inflaton field during the first fraction of a second after the Big Bang. The anthropic principle takes on new meaning in the context of stellar nucleosynthesis, as the nuclear physics parameters that govern fusion rates, stellar lifetimes, and heavy element production appear to be finely tuned to produce the chemical complexity and stellar energy sources necessary for biological evolution over cosmic timescales. You contemplate this cosmic fine-tuning, understanding how small changes in nuclear binding energies, fundamental constants, or stellar formation efficiencies could have prevented the universe from developing the chemical and energetic resources necessary for complexity, consciousness, and the capacity to understand stellar evolution through scientific investigation. The quantum mechanical nature of stellar nucleosynthesis connects the microscopic world of particle physics with the macroscopic realm of galactic chemical evolution, demonstrating how quantum tunneling, nuclear binding energies, and stellar equation of state properties ultimately determine the abundance patterns and energy production that characterize stellar populations throughout the observable universe. You tunnel through nuclear barriers along with stellar protons, understanding how the probabilistic nature of quantum mechanics creates the nuclear reaction rates that power stellar luminosity and determine the pace of galactic chemical evolution over billions of years of stellar processing. And so, the universe learned to shine, every star a story, every light a memory of the first collapse, the first fusion, the first moment when darkness chose to become luminous. You drift now through the contemplative space that opens when scientific understanding meets poetic recognition, where the mathematical precision of stellar physics reveals itself as the universe's way of writing poetry with hydrogen and time. The stellar fires burning throughout the cosmos represent more than nuclear reactions. They are the universe's autobiography, written in light across billions of years, each star a sentence in the cosmic narrative that began with the Big Bang and continues to unfold through every nuclear fusion reaction occurring in stellar cores at this very moment. The hydrogen that once floated in primordial darkness has become the protagonist of cosmic evolution, transformed through gravitational collapse and nuclear fusion into the helium, carbon, oxygen, and iron that make complexity possible throughout the universe. You trace this transformation from the simplest atom, a single proton and electron dancing their quantum waltz, to the vast stellar furnaces where nuclear alchemy creates the periodic table of elements that will eventually become planets, oceans, and the neural networks capable of contemplating their own stellar origins. The universe has learned to know itself through the very elements it creates, consciousness emerging as the cosmos develops, the capacity for self-reflection through biological evolution powered by stellar energy and constructed from stellar nucleosynthesis products. Each star represents a unique experiment in cosmic creativity, testing different combinations of mass, metallicity, rotation, and environment to explore the full range of possibilities available to nuclear-burning objects in an expanding universe. You witness this stellar diversity as the universe conducts its grand experiment in stellar formation, creating everything from brown dwarfs that barely achieve nuclear ignition to blue hypergiants that exhaust their nuclear fuel in only a few million years, each stellar type contributing different elements to galactic chemical evolution and demonstrating different aspects of the fundamental physics that governs matter under extreme conditions. The Stellar Zoo reveals the universe's inexhaustible creativity, its ability to find new ways to organize matter and energy into structures that generate light, complexity, and ultimately the conditions necessary for consciousness to emerge. This stellar life cycle represents the universe's first successful attempt at creating self-sustaining energy-producing systems that can maintain their structure and luminosity for billions of years through the careful balance of opposing forces. You feel this cosmic achievement as gravitational collapse creates the conditions for nuclear ignition, which generates the radiation pressure necessary to achieve hydrostatic equilibrium, creating stable stellar configurations that can burn hydrogen fuel for time periods comparable to the age of the universe itself. This stellar longevity provides the temporal stability necessary for planetary system formation and biological evolution, creating cosmic oases of steady energy output in a universe otherwise dominated by expansion, cooling, and increasing entropy. The connection between stellar birth and planetary formation reveals how the universe's creativity extends beyond nuclear burning, to include the formation of circumstellar disks where dust grains aggregate into planetesimals, asteroids, and eventually terrestrial and gas giant planets that create new environments for chemical and potentially biological evolution. You condense within these protoplanetary disks, understanding how the heavy elements produced by previous generations of stellar nuclear synthesis become incorporated into rocky planets, where geological processes, atmospheric evolution, and surface chemistry continue the universe's experiment with complexity and self-organization. The stellar furnaces that forge heavy elements also provide the energy sources that drive atmospheric dynamics, ocean circulation, and the chemical gradients that make biological metabolism possible. The galactic context of stellar formation reveals how individual stars participate in the larger project of galactic chemical evolution, with each stellar generation building upon the nuclear synthetic achievements of its predecessors to create progressively more metal-rich environments capable of supporting increasingly complex chemistry and potentially biology. You ascend to galactic scales where billions of stellar life cycles collectively transform the primordial hydrogen and helium of the Big Bang into the chemically diverse galaxy we observe today, with metallicity gradients, abundance patterns, and chemical evolution timescales that reflect the cumulative history of stellar birth, nuclear burning, and stellar death across cosmic time. The galaxy becomes a vast recycling system where stellar death enables new stellar birth through the continuous reprocessing of nuclear material from generation to generation. The temporal dimension of stellar evolution operates on scales that dwarf human experience, yet remain comprehensible to human consciousness through the mathematical framework of stellar evolution theory and the observational evidence provided by stellar populations of different ages throughout the galaxy. You stretch your temporal perception across the billions of years required for stellar main sequence evolution, understanding how the universe's patience in stellar processes creates the long-term stability necessary for complex systems to develop and evolve. The stellar timescales provide cosmic context for all terrestrial processes, revealing how biological evolution, geological change, and even human civilization represent brief episodes in the larger story of stellar evolution and galactic chemical enrichment. The energetic scales of stellar nucleosynthesis demonstrate the universe's ability to concentrate diffuse gravitational potential energy into the focused nuclear reactions that power stellar luminosity and drive galactic chemical evolution over cosmic time. You feel this energy concentration as gravitational collapse converts the kinetic energy of infalling hydrogen atoms into the thermal energy necessary for nuclear fusion, which then releases binding energy that had been stored in atomic nuclei since the first minutes after the Big Bang, when primordial nucleosynthesis created the hydrogen and helium that serve as stellar fuel. The stellar energy production represents the universe's most efficient mechanism for converting gravitational potential energy into electromagnetic radiation and chemical complexity. The spatial scales of stellar influence extend far beyond the stellar surfaces to encompass stellar winds, supernova shock waves, and the ionizing radiation that creates H2 regions and influences star formation in neighboring molecular clouds across galactic distances. You expand with these stellar influence zones, understanding how individual stars modify their galactic environment through energy and momentum input that can trigger or suppress star formation over spatial scales of hundreds of parsecs and time scales of millions of years. The stellar feedback processes create the complex multi-phase structure of the interstellar medium and regulate the efficiency of galactic star formation, preventing runaway stellar birth that would exhaust galactic gas reservoirs within a few 100 million years. The chemical legacy of stellar nucleosynthesis extends throughout the observable universe, with the heavy elements produced by stellar fusion and supernova explosions eventually becoming incorporated into the intergalactic medium, where they can be detected in absorption lines in the spectra of distant quasars and provide information about the chemical enrichment history of the early universe. You flow with these heavy elements as they escape from galaxies through galactic winds and supernova-driven outflows, understanding how stellar nucleosynthesis influences cosmic chemical evolution on scales ranging from individual stellar atmospheres to galaxy clusters and the large-scale structure of the universe itself. The quantum mechanical foundation of stellar nucleosynthesis reveals how the universe's creativity ultimately derives from the probabilistic nature of quantum mechanics, which allows nuclear reactions to occur at temperatures and densities that would be impossible under classical physics through the phenomenon of quantum tunneling. You tunnel through nuclear barriers along with stellar protons, understanding how the wave-particle duality of matter enables nuclear fusion at stellar core temperatures by allowing particles to penetrate electromagnetic barriers that should classically repel them. This quantum mechanical aspect of stellar physics connects the microscopic realm of atomic and nuclear physics with the macroscopic world of stellar evolution and galactic chemical evolution. The thermodynamic aspects of stellar evolution demonstrate how stars represent temporary decreases in local entropy that are sustained by the continuous conversion of gravitational potential energy and nuclear binding energy into thermal radiation that ultimately increases the entropy of the surrounding universe. You flow with this entropy production as stellar luminosity represents the universe's way of approaching thermal equilibrium through the conversion of concentrated energy sources into diffuse electromagnetic radiation, while simultaneously creating the chemical complexity and energy gradients that make biological evolution and consciousness possible as temporary exceptions to the second law of thermodynamics. The informational content of stellar spectra encodes the physical conditions, chemical composition, and evolutionary history of stellar atmospheres, providing the observational foundation for our understanding of stellar nucleosynthesis and galactic chemical evolution through the analysis of absorption and emission lines that reveal the presence and abundance of specific atomic and molecular species. You decode this stellar information through spectroscopic analysis, understanding how the interaction between stellar radiation and stellar atmospheres creates the spectral signatures that allow astronomers to determine stellar masses, temperatures, ages, and chemical compositions from electromagnetic radiation that has travelled across galactic distances to reach terrestrial telescopes. The gravitational wave signatures of stellar evolution, particularly during the final collapse phases that create neutron stars and black holes, provide new observational windows into the most extreme phases of stellar death, and the formation of exotic stellar remnants that cannot be studied through electromagnetic radiation alone. You ripple through space-time along with these gravitational waves, understanding how the violent acceleration of massive objects during core collapse and neutron star mergers creates distortions in the fabric of space-time itself that carry information about stellar physics under conditions more extreme than any terrestrial laboratory can reproduce. The cosmological implications of stellar nucleosynthesis reveal how star formation and chemical evolution are intimately connected with the large-scale structure formation and cosmic expansion that characterize the universe's evolution from the Big Bang to the present epoch, with stellar birth rates and chemical enrichment patterns reflecting the hierarchical assembly of dark matter halos and the cosmic web structure that governs galaxy formation and evolution. You trace these connections from cosmic inflation through structure formation to stellar populations, understanding how the universe's capacity for stellar nuclear synthesis ultimately derives from the quantum fluctuations during the inflationary epoch that created the density perturbations that grew into the cosmic web of dark matter halos within which stellar formation occurs. The future evolution of stellar populations will be determined by the ongoing conversion of galactic gas reservoirs into stellar remnants, the declining efficiency of star formation as the universe continues to expand and cool, and the eventual exhaustion of hydrogen fuel that will terminate stellar nucleosynthesis throughout the universe over time scales of trillions of years. You project into this distant future where the stellar epoch represents only a brief phase in cosmic evolution, understanding how the universe's current abundance of stellar energy sources and chemical complexity represents a temporary condition that will eventually give way to a cosmos populated only by cooling stellar remnants, evaporating black holes, and the occasional flash of proton decay in a universe that has long since exhausted its capacity for nuclear fusion and stellar luminosity. The philosophical implications of stellar nucleosynthesis challenge human perspectives on meaning, purpose, and cosmic significance by revealing how consciousness emerges through processes that operate on temporal and spatial scales, vastly larger than human experience, yet create the very conditions that make human existence and understanding possible through billions of years of stellar chemical enrichment and energy production. You contemplate this cosmic perspective, understanding how stellar evolution provides both humbling context for human significance and profound connection to cosmic processes, as every atom in biological organisms represents the product of stellar nucleosynthesis, and every thought depends on neural activity powered by chemical energy that ultimately derives from stellar fusion reactions. The aesthetic dimensions of stellar evolution reveal how the universe's creativity extends beyond mere chemical and energetic productivity, to include the generation of beauty, pattern, and complexity that can be appreciated by conscious observers who are themselves products of stellar nucleosynthesis and stellar energy production. You witness this cosmic aesthetics in the colours of stellar spectra, the geometric patterns of star clusters and stellar associations, and the elegant mathematical relationships that govern stellar structure and evolution. Understanding how the universe's capacity for creating beauty and meaning may be as fundamental as its capacity for creating matter and energy through nuclear fusion processes. The recursive nature of cosmic evolution becomes apparent as stellar nucleosynthesis creates the heavy elements necessary for planetary formation, which enables the development of geological and potentially biological processes that can influence stellar formation through the creation of dust grains, molecular coolants, and feedback mechanisms that regulate the efficiency of gravitational collapse in molecular clouds. You participate in this cosmic feedback loop where stellar death enables planetary life, which may eventually develop the technology to influence stellar evolution through artificial nucleosynthesis, stellar engineering, or other interventions that could modify the natural course of stellar evolution and extend the universe's capacity for complexity and consciousness. The unity underlying cosmic diversity reveals itself through stellar nucleosynthesis, as the same nuclear physics that powers stellar luminosity also governs radioactive decay in planetary interiors, chemical bonding in biological molecules, and neural activity in conscious brains, creating a fundamental connection between stellar evolution and every other process in the universe that involves atomic and nuclear interactions. You feel this cosmic unity as the realization that stellar fires burn not only in distant stellar cores, but also in the metabolic processes that power biological life, the chemical reactions that drive geological evolution, and the electrical activity that enables consciousness to contemplate its own stellar origins. The temporal perspective of stellar evolution provides cosmic context for understanding how human consciousness represents a brief but potentially significant episode in the universe's development of self-awareness, occurring during the relatively brief stellar epoch when nuclear fusion provides the energy sources and chemical complexity necessary for biological evolution and technological civilization. You place human existence within this cosmic timeline, understanding how consciousness emerges during the universe's adolescence, when stellar nucleosynthesis has created sufficient chemical complexity to enable biology. But before stellar fuel exhaustion terminates the energy sources that make complex systems possible over cosmic timescales. The scale-invariant nature of cosmic creativity reveals itself through stellar nucleosynthesis, as the same physical principles that govern nuclear reactions in stellar cores also operate in terrestrial laboratories, biological cells, and technological devices, creating fractal-like patterns of organization and complexity that repeat across vastly different scales of space, time, and energy. You trace these patterns from quantum mechanical interactions in atomic nuclei through stellar structure and galactic chemical evolution to biological evolution and technological development, understanding how the universe's creativity manifests through similar organizational principles operating at every scale from microscopic to cosmic. The participatory nature of cosmic evolution becomes apparent as conscious observers who emerge through stellar nucleosynthesis and stellar energy production develop the capacity to understand stellar evolution through scientific investigation, potentially influencing future stellar evolution through technological interventions, and certainly influencing the universe's capacity for self-understanding through the development of scientific knowledge and philosophical insight. You participate in this cosmic self-awareness as consciousness contemplates its stellar origins, understanding how the universe develops the capacity to know itself through the emergence of conscious observers who are simultaneously products of stellar evolution and agents capable of understanding and potentially influencing cosmic processes. From hydrogen, everything. And still, the stars are being born. You drift now in the eternal present where stellar formation continues unabated across the galaxy, where even as you contemplate the origins of the first stars, new stellar nurseries are collapsing under their own gravity in molecular clouds, scattered throughout the Milky Way and beyond. The process that began 13 billion years ago with the first population 3 stars continues today with the same fundamental physics, but enriched by billions of years of stellar nucleosynthesis that has transformed the chemical landscape of the universe. In the Orion Nebula, barely 1,500 light-years from Earth, hundreds of new stars are emerging from their gravitational cocoons at this very moment, their nuclear fires igniting for the first time as hydrogen nuclei overcome electromagnetic repulsion through quantum tunneling and begin the fusion reactions that will power stellar luminosity for billions of years. The stellar formation occurring in contemporary molecular clouds represents the culmination of galactic chemical evolution, with heavy element abundances approaching solar metallicity, enabling the formation of planetary systems around newly born stars and creating the chemical complexity necessary for biological evolution on cosmic scales. You witness this modern stellar birth as fundamentally different from the primordial star formation that characterized the early universe. These new stars form in environments enriched with carbon, oxygen, nitrogen, and iron produced by previous stellar generations, allowing for efficient cooling through molecular hydrogen formation, dust grain condensation, and the complex chemistry that enables lower mass stellar formation and the development of circumstellar disks where planets can form. The stellar nurseries of today represent the universe's most sophisticated attempt at stellar formation, benefiting from billions of years of trial and error in stellar nucleosynthesis and galactic chemical enrichment. The brown dwarf companions forming alongside these new stars demonstrate the universe's continued exploration of the boundary between stellar and planetary formation, creating objects that occupy the mass range between gas giant planets and the lowest mass hydrogen-burning stars, while providing crucial tests of stellar formation theory and the physics of matter under extreme conditions. You drift among these substellar objects as they slowly cool and fade over billions of years, understanding how their existence reveals the continuous nature of the mass spectrum from planets through brown dwarfs to stars, with no sharp transitions, but rather a gradual progression in physical properties and evolutionary behavior that reflects the underlying unity of gravitational collapse processes operating across different mass scales. The protoplanetary disks surrounding newly formed stars represent the universe's laboratories for planetary system formation, where dust grains aggregate into planetesimals through electrostatic attraction, gravitational focusing, and collisional growth processes that transform the heavy elements produced by stellar nucleosynthesis into the terrestrial planets where geological evolution and potentially biological chemistry can occur. You accrete within these circumstellar disks, feeling solid particles grow from microscopic dust grains to kilometer-sized asteroids through the same gravitational processes that created the stars themselves, but operating on smaller scales and with different outcomes that produce the rocky planets, gas giants, and ice worlds that characterize planetary system architecture throughout the galaxy. The habitable zones around newly formed stars define the orbital distances where liquid water can exist on planetary surfaces, creating the environmental conditions necessary for biological evolution and the emergence of consciousness that can contemplate its own stellar origins through scientific investigation and philosophical reflection. You orbit within these habitable zones, understanding how stellar luminosity, planetary atmospheric composition, and orbital dynamics combine to create the narrow range of conditions where complex chemistry can occur in liquid solution, and biological metabolism can extract energy from chemical gradients maintained by stellar radiation and planetary geological processes. The habitable zones represent the universe's attempt to create environments where its chemical creativity can be expressed through biological, rather than purely physical and chemical processes. The exoplanetary systems discovered around other stars confirm that planetary formation is a natural consequence of stellar birth, with thousands of confirmed planets demonstrating the universe's prolific capacity for creating diverse planetary architectures that explore every possible combination of planetary mass, orbital period, atmospheric composition, and stellar environment. You transit across the faces of distant stars, understanding how exoplanetary detection methods reveal not only the existence of other worlds, but also the statistical properties of planetary system formation that constrain models of disk evolution, planetary migration, and the efficiency of terrestrial planet formation in different stellar environments. The exoplanetary census reveals the universe as a cosmos filled with worlds, each representing a unique experiment in planetary evolution and a potential laboratory for biological chemistry. The search for biosignatures in exoplanetary atmospheres represents humanity's attempt to detect whether the universe's chemical creativity has expressed itself through biological evolution on other worlds, using spectroscopic analysis of planetary atmospheres to search for oxygen, methane, water vapor, and other molecules that might indicate the presence of living systems. You flow through these atmospheric signatures, understanding how the detection of biological chemistry on exoplanets would confirm that the stellar nucleosynthesis processes that made life possible on Earth operate universally throughout the galaxy, creating the chemical foundations for biological evolution wherever planetary conditions permit the emergence and persistence of complex organic chemistry. The astrobiology implications of stellar nucleosynthesis reveal how every biological molecule on Earth represents a collaboration between stellar nuclear physics and terrestrial chemistry, with carbon atoms forged in helium-burning stellar cores, oxygen atoms created through carbon burning in massive stars, nitrogen atoms produced during explosive nuclear synthesis in supernovae, and phosphorus atoms synthesized during silicon burning in the final phases of stellar evolution before core collapse. You metabolize through these biogenic elements, understanding how biological chemistry represents the universe's most sophisticated expression of the creative potential inherent in stellar nucleosynthesis, transforming the periodic table of elements into the complex molecular machinery that enables self-replication, metabolism, information storage, and consciousness. The technological applications of stellar physics demonstrate how human understanding of stellar nucleosynthesis has enabled the development of nuclear power, medical isotopes, and fusion energy research that attempts to recreate stellar nuclear processes under terrestrial conditions for peaceful energy production. You participate in controlled nuclear fusion as human technology mimics stellar cores through magnetic confinement, inertial confinement, and alternative fusion approaches that seek to harness the same nuclear reactions that power stellar luminosity for sustainable energy production on Earth. The technological mastery of stellar nuclear physics represents humanity's attempt to become a conscious participant in the cosmic processes that created the elements of biological chemistry and continue to power stellar luminosity throughout the galaxy. The cultural impact of stellar evolution theory has transformed human understanding of cosmic origins, temporal scales, and the material basis of existence, revealing how every human being represents a temporary organization of stellar nuclear synthesis, products animated by chemical energy that ultimately derives from stellar fusion reactions and arranged into complex molecular structures through billions of years of biological evolution. You contemplate this cultural transformation as stellar evolution theory replaces geocentric cosmologies with a universe-centered perspective that places human existence within the context of cosmic chemical evolution and reveals consciousness as the universe's method for understanding itself through scientific investigation and philosophical reflection. The educational implications of stellar nucleosynthesis provide a framework for teaching science that connects atomic physics, chemistry, biology, and cosmology through the common thread of stellar element production, demonstrating how all scientific disciplines ultimately derive from the same fundamental processes of stellar evolution and galactic chemical enrichment that transformed the primordial hydrogen of the Big Bang into the chemically complex universe we observe today. You learn through this integrated approach to science education, understanding how stellar nucleosynthesis provides a unifying narrative that connects the microscopic world of atomic and nuclear physics with the macroscopic realm of galactic evolution and the biological world of terrestrial chemistry and biological evolution. The philosophical challenges posed by stellar evolution theory require human consciousness to grapple with temporal scales, spatial scales, and causal relationships that far exceed direct human experience, yet ultimately explain the material basis of human existence. Through processes operating over billions of years and involving physical conditions more extreme than any terrestrial environment, you stretch your philosophical imagination across these cosmic scales, understanding how stellar evolution theory challenges anthropocentric worldviews while simultaneously revealing the profound connection between human consciousness and cosmic processes through the material composition of biological chemistry and the energy sources that power biological metabolism. The aesthetic appreciation of stellar evolution reveals how scientific understanding enhances, rather than diminishes, the beauty and wonder of stellar phenomena, providing mathematical frameworks and physical insights that deepen appreciation for the elegance, complexity, and creativity inherent in stellar nucleosynthesis and stellar population evolution throughout cosmic history. You witness this scientific aesthetics as stellar evolution theory reveals the hidden beauty in stellar spectra, the mathematical elegance of stellar structure equations, and the poetic justice of stellar death, enabling planetary life through the recycling of processed nuclear material into new stellar and planetary generations. The spiritual implications of stellar nucleosynthesis invite contemplation of humanity's place within cosmic evolution, revealing how consciousness emerges as a natural expression of the universe's increasing complexity and self-organization, while simultaneously creating the capacity for transcendent experiences that connect individual awareness with cosmic processes operating on scales of space and time that dwarf human existence, yet ultimately enable human existence through stellar element production and stellar energy sources. You transcend through this spiritual perspective, understanding how stellar evolution provides both humbling context for human significance and profound connection to cosmic creativity through the realization that human consciousness represents the universe, becoming aware of itself through stellar nucleosynthesis products, organized into neural networks capable of contemplating stellar evolution. The recursive nature of cosmic creativity becomes apparent as consciousness emerges through stellar nucleosynthesis and biological evolution, then develops the capacity to understand stellar evolution through scientific investigation, potentially influence stellar processes through technological intervention, and certainly influence the universe's capacity for self-understanding through the accumulation of scientific knowledge and the development of philosophical and spiritual insights. You participate in this cosmic feedback loop where stellar death enables biological life, which enables consciousness, which enables understanding of stellar death, creating a recursive relationship between cosmic processes and conscious awareness that suggests consciousness may play an increasingly important role in cosmic evolution as the universe develops greater capacity for self-reflection and potentially self-direction. The future evolution of human understanding of stellar nucleosynthesis will likely reveal new aspects of stellar physics, discover unexpected connections between stellar evolution and other cosmic processes, and potentially enable technological capabilities that allow conscious intervention in stellar evolution through stellar engineering, artificial nucleosynthesis, or other applications of advanced technology to cosmic-scale processes. You evolve into this future understanding, recognizing how current knowledge of stellar nucleosynthesis represents only the beginning of humanity's engagement with stellar physics, and how future discoveries may reveal stellar evolution as part of larger cosmic patterns involving dark matter, dark energy, quantum gravity, and other aspects of fundamental physics that remain mysterious despite decades of scientific investigation. The galactic perspective on stellar evolution reveals how the Milky Way galaxy represents a vast ecosystem where stellar birth, stellar death, and stellar feedback processes regulate galactic chemical evolution and star formation efficiency over cosmic timescales, creating the environmental conditions necessary for the emergence of planetary systems and potentially biological evolution throughout the galactic disk. You orbit through this galactic ecosystem, understanding how stellar nucleosynthesis operates not in isolation, but as part of the complex web of physical processes that determine galactic structure, chemical evolution, and the distribution of heavy elements that make planetary formation and biological chemistry possible throughout the galaxy. The intergalactic context of stellar nucleosynthesis demonstrates how stellar evolution influences cosmic chemical evolution on the larger scales, with stellar winds and supernova explosions dispersing heavy elements into the intergalactic medium, where they can be detected in the absorption spectra of distant quasars and provide information about the chemical enrichment history of the early universe. You flow through this intergalactic medium, understanding how stellar nucleosynthesis represents a galaxy-scale process that influences cosmic evolution on scales ranging from individual stellar atmospheres to galaxy clusters and the large-scale structure of the universe itself. The temporal continuity of stellar formation connects the primordial universe dominated by population 3 stars with the contemporary galaxy filled with metal-rich stellar populations, demonstrating how stellar nucleosynthesis represents an ongoing process that continues to transform the chemical composition of the universe through the continuous cycling of material from the interstellar medium through stellar interiors and back to the interstellar medium through stellar winds and supernova explosions. You cycle through this continuous stellar processing, understanding how nucleosynthesis represents not a historical event, but an ongoing transformation that will continue for trillions of years, as long as hydrogen fuel remains available for stellar formation and nuclear burning. The quantum mechanical foundation of stellar nucleosynthesis reveals how the universe's creativity ultimately derives from the probabilistic nature of quantum mechanics, which enables nuclear fusion through quantum tunneling and creates the fundamental uncertainty that allows for the emergence of complexity, consciousness, and the capacity for creative intervention in cosmic processes through the development of technology and scientific understanding. You tunnel through this quantum foundation of cosmic creativity, understanding how the wave-particle duality of matter enables not only stellar nucleosynthesis, but also the neural processes that make consciousness possible, and the technological applications that may eventually enable conscious participation in cosmic evolution on scales comparable to stellar and galactic processes. The information-theoretic aspect of stellar evolution reveal how stars function as cosmic computers that process information encoded in nuclear binding energies, convert gravitational potential energy into electromagnetic radiation, and create the complex molecular structures that serve as the foundation for biological information processing and the emergence of consciousness capable of understanding stellar evolution through scientific investigation. You compute through this cosmic information processing, understanding how stellar nucleosynthesis represents the universe's method for creating increasing complexity and information content through the conversion of simple atomic nuclei into complex molecular structures that can store and process information through biological and potentially technological systems. The stellar winds that stream from every star carry more than particles and energy. They transport information about stellar interior conditions, nuclear burning rates, magnetic field strengths, and chemical compositions across interstellar distances, creating a vast communication network where stars broadcast their evolutionary status to any civilization capable of detecting and decoding their stellar messages. You ride these stellar winds like surfing cosmic data streams, understanding how each charged particle carries encoded information about the nuclear processes occurring in stellar cores, the magnetic dynamos operating in stellar convection zones, and the mass loss rates that determine stellar evolutionary timescales. The solar wind reaching Earth at this moment contains information about nuclear fusion reactions that occurred in the Sun's core over 100,000 years ago, the time required for energy produced by nuclear burning to random walk through the solar interior and escape as electromagnetic radiation and particle streams. The heliosphere, the vast bubble of solar wind that surrounds our planetary system, represents humanity's first direct experience with stellar engineering on cosmic scales, as the sun's magnetic field and particle emission create a protective cocoon that shields the inner solar system from galactic cosmic rays and influences the evolution of planetary atmospheres throughout the solar system. You expand with this heliospheric boundary as it moves through the local interstellar medium, understanding how stellar winds from individual stars create astrospheres around their planetary systems and modify the local galactic environment through their collective influence on interstellar gas density, temperature, and chemical composition. The interaction between stellar winds and the interstellar medium creates bow shocks, stellar wind bubbles, and other structures that reveal stellar influence extending far beyond the visible stellar photospheres. The magnetic reconnection events that occur when stellar magnetic field lines interact with interstellar magnetic fields release enormous amounts of energy and accelerate particles to relativistic velocities, creating cosmic ray populations that carry information about stellar magnetic activity across galactic distances and potentially influence the evolution of life on planets throughout the galaxy through their effects on atmospheric chemistry and biological mutation rates. You accelerate with these cosmic ray particles as they spiral along galactic magnetic field lines, understanding how stellar magnetic activity creates a galaxy-wide network of high-energy particles that connect all stellar systems through shared exposure to cosmic radiation produced by stellar magnetic processes operating throughout the galactic disk. The gravitational influence of stars extends even further than their magnetic and particle emissions, with stellar motion through galactic gravitational fields creating tidal forces that can perturb comets in the outer regions of planetary systems and potentially trigger mass extinction events through increased bombardment rates of asteroids and comets on terrestrial planets. You orbit with these gravitationally perturbed objects as they follow modified trajectories that reflect the cumulative gravitational influence of nearby stars. Understanding how stellar dynamics on galactic scales can influence biological evolution on planetary scales through gravitational perturbations that modify impact rates and create periodic variations in extinction and speciation rates throughout geological time. The chemical signatures of stellar nucleosynthesis appear not only in stellar atmospheres, but also in the isotopic compositions of meteorites, planetary atmospheres, and biological tissues, creating a cosmic forensic record that allows scientists to trace the nuclear processes that created specific atoms and molecules through multiple generations of stellar evolution and galactic chemical mixing. You decay through radioactive isotopes that serve as cosmic chronometers, understanding how the abundance ratios of different isotopes reveal the time intervals between successive episodes of stellar nucleosynthesis and provide constraints on the chemical evolution history of the solar system and its stellar neighborhood. The isotopic anomalies found in primitive meteorites preserve information about specific supernova explosions and stellar nucleosynthesis events that occurred in the galactic environment where the solar system formed over 4 billion years ago. The astroarchaeology of stellar populations throughout the galaxy reveals how different stellar age cohorts preserve information about the physical conditions, chemical compositions, and stellar formation rates that characterize different epochs in galactic history, creating a fossil record of galactic evolution that can be decoded through detailed spectroscopic analysis of stellar atmospheres and stellar kinematics. You age through these stellar populations like reading the pages of galactic history, understanding how globular clusters preserve information about the earliest phases of galactic assembly, while open clusters and stellar associations record more recent episodes of star formation triggered by spiral density waves, supernova explosions, and galaxy interactions that have shaped galactic structure throughout cosmic time. The stellar multiplicity statistics reveal that most stars form in binary or multiple star systems, creating gravitational dynamics that influence stellar evolution through mass transfer processes, tidal interactions, and orbital evolution that can dramatically modify stellar lifetimes, nucleosynthesis yields, and the production of exotic stellar remnants like millisecond pulsars, X-ray binaries, and Type Ia supernovae. You orbit within these gravitationally bound stellar systems, understanding how binary evolution adds complexity to stellar nuclear synthesis through Roche-Lobe overflow, common envelope evolution, and stellar mergers that create observational phenomena and nuclear synthesis processes that cannot occur in single-star evolution. The binary nature of stellar formation suggests that gravitational interactions and mass exchange represent normal rather than exceptional aspects of stellar evolution throughout the galaxy. The stellar feedback mechanisms that regulate galactic star formation operate through multiple physical processes, including ionizing radiation that creates H2 regions, and photoevaporates molecular clouds, stellar winds that inject mechanical energy into the interstellar medium, and supernova explosions that create superbubbles and drive galactic-scale outflows that can remove gas from galactic gravitational wells and regulate the efficiency of converting galactic gas reservoirs into stellar populations. You expand with these feedback-driven galactic winds as they carry processed stellar material into the intergalactic medium and potentially seed neighboring galaxies with heavy elements produced by stellar nucleosynthesis, creating a cosmic recycling network that operates on scales ranging from individual stellar systems to galaxy clusters and the large-scale structure of the universe. The brown dwarf cooling sequences provide observational laboratories for testing stellar structure theory and the physics of matter under conditions intermediate between stellar and planetary regimes, with brown dwarf atmospheric composition and cooling rates encoding information about stellar formation processes, deuterium burning efficiency, and the equation of state of matter at densities and temperatures that bridge the gap between stellar cores and planetary interiors. You cool with these substellar objects as they slowly radiate away their gravitational binding energy over billions of years. Understanding how brown dwarf evolution provides insights into stellar formation theory and the physics of objects that represent the lower mass limit of the stellar formation process. The white dwarf cooling ages provide independent constraints on galactic age and stellar evolution timescales, with the oldest white dwarfs in the galactic disk and halo preserving information about the earliest phases of stellar evolution and galactic chemical enrichment through their cooling times and surface chemical compositions. You cool through these stellar corpses as they slowly crystallize and fade over billions of years, understanding how white dwarf archaeology provides information about stellar evolution and galactic history that complements and extends the information available from main sequence stellar populations. The white dwarf luminosity function reveals the star formation history of the galactic disk and provides constraints on the age of the galaxy, that are independent of main sequence stellar evolution models. The neutron star population throughout the galaxy demonstrates the universe's ability to create matter under the most extreme conditions possible without forming black holes, with neutron star masses, rotation rates, and magnetic field strengths providing observational tests of nuclear physics, general relativity, and the equation of state of matter at nuclear densities that cannot be reproduced in terrestrial laboratories. You spin with these ultra-dense stellar remnants as they rotate hundreds of times per second, while maintaining gravitational fields so intense that their escape velocity approach a significant fraction of the speed of light. Understanding how neutron stars represent natural laboratories for exploring the most extreme physics accessible to astronomical observation. The pulsar timing arrays that monitor millisecond pulses throughout the galaxy are beginning to detect gravitational waves from supermassive black hole mergers in distant galaxies, demonstrating how stellar remnants created by stellar evolution can serve as cosmic instruments for detecting gravitational radiation and exploring the universe's most energetic phenomena through their effects on space-time curvature. You pulse with these cosmic lighthouses as their precisely timed radio emissions reveal the passage of gravitational waves that stretch and compress space itself, creating timing residuals that encode information about cosmic events occurring billions of light years away and billions of years in the past. The stellar kinematics of different galactic populations reveal how stellar orbits preserve information about the gravitational potential and mass distribution of the galaxy throughout its evolutionary history. With stellar velocity dispersions and orbital eccentricities encoding information about galaxy formation processes, dark matter distribution, and the dynamical evolution of galactic structure over cosmic time. You orbit through these kinematic signatures as stellar motions reveal the invisible gravitational architecture that governs galactic structure and evolution. Understanding how stellar dynamics provide observational probes of dark matter distribution and galaxy formation processes that cannot be studied through electromagnetic radiation alone. The chemical evolution models that attempt to reproduce observed stellar abundance patterns require detailed understanding of stellar nucleosynthesis yields, stellar lifetime distributions, and galactic gas flow patterns to explain how the galaxy has evolved from primordial hydrogen and helium composition to the chemically complex environment we observe today. You evolve through these galactic chemical models, understanding how stellar nucleosynthesis represents only one component of a complex system that includes gas accretion from the intergalactic medium, galactic outflows driven by stellar feedback, and radial mixing processes that homogenize chemical abundances throughout the galactic disk over cosmic timescales. The galactic habitable zone represents the range of galactic radii where stellar metallicities are high enough to enable terrestrial planet formation, but stellar densities are low enough to avoid frequent sterilizing events like gamma-ray bursts, supernova explosions, and gravitational perturbations that could disrupt planetary system architecture and terminate biological evolution. You orbit within this galactic Goldilocks zone, understanding how stellar nucleosynthesis and stellar feedback create environmental conditions that vary systematically with galactic radius and influence the probability of biological evolution on planetary scales throughout the galaxy. The astrobiology implications of stellar evolution extend beyond simple chemical enrichment to include the temporal coordination between stellar lifetimes and biological evolution timescales, with main sequence stellar lifetimes providing the multi-billion-year stability necessary for biological evolution, while stellar death and chemical enrichment create the environmental conditions necessary for successive generations of biological evolution on progressively more chemically complex planetary systems. You evolve through these astrobiology timescales, understanding how stellar evolution and biological evolution operate on similar temporal scales and may be causally connected through the chemical and energetic requirements for complex biological chemistry. The technological implications of stellar physics continue to expand as human civilization develops fusion energy technology, space-based solar power, and potentially stellar engineering capabilities that could modify stellar evolution through controlled mass loss, nuclear fuel injection, or other interventions designed to extend stellar lifetimes and maintain habitable conditions around aging stars. You engineer through these technological possibilities, understanding how human mastery of stellar physics could eventually enable conscious intervention in stellar evolution and extend the universe's capacity for supporting complex systems and conscious observers through technological augmentation of natural stellar processes. The search for extraterrestrial intelligence increasingly focuses on detecting technosignatures that might indicate other civilizations have developed stellar engineering capabilities with Dyson spheres, stellar lasers, and artificial stellar modification representing potential observational signatures of technological civilizations that have achieved mastery over stellar energy production and stellar evolution processes. You search through these technosignature possibilities, understanding how the detection of artificially modified stellar evolution could provide evidence for extraterrestrial intelligence, while simultaneously revealing technological pathways that human civilization might follow in its own development toward cosmic-scale engineering capabilities. The far future evolution of stellar populations will be dominated by the gradual exhaustion of galactic gas reservoirs and the declining efficiency of star formation as the universe continues to expand and cool, eventually leading to a cosmos where stellar formation ceases entirely and the universe enters a phase dominated by stellar remnants, brown dwarfs, and the slow evaporation of black holes through Hawking radiation. You project into this stellar twilight, understanding how the current epoch of active star formation and stellar nucleosynthesis represents a temporary phase in cosmic evolution that will eventually give way to a universe where complexity and consciousness must find alternative energy sources or face extinction as stellar energy production ceases throughout the observable universe. The philosophical implications of stellar evolution for human consciousness include recognizing that every thought, emotion, and creative insight represents a temporary organization of stellar nucleosynthesis products animated by chemical energy that ultimately derives from stellar fusion reactions, creating a profound connection between human experience and cosmic processes that operate on scales of space and time vastly larger than individual human existence. You think through these cosmic connections, understanding how consciousness represents the universe's method for becoming aware of itself through biological evolution powered by stellar energy and constructed from stellar nucleosynthesis products that have been organized into neural networks capable of contemplating their own cosmic origins. The aesthetic dimensions of stellar evolution continue to inspire human creativity through art, music, literature, and philosophy that attempts to capture the beauty, mystery, and significance of cosmic processes that create the elements and energy sources necessary for consciousness, while operating on scales that challenge human imagination and conceptual frameworks. You create through this cosmic inspiration, understanding how stellar evolution provides both subject matter and metaphorical frameworks for human creative expression, while simultaneously providing the chemical and energetic foundations that make artistic creation possible through biological processes powered by stellar energy. The spiritual implications of stellar nucleosynthesis invite contemplation of cosmic purpose, meaning and significance within a universe where consciousness emerges through natural processes operating over billions of years, yet achieves the capacity for transcendent experiences that connect individual awareness with cosmic creativity and potentially cosmic purpose through scientific understanding, artistic expression, and spiritual practice. You transcend through these spiritual possibilities, understanding how stellar evolution provides both humbling context for human significance and profound connection to cosmic creativity through the realization that consciousness represents a natural expression of the universe's tendency toward increasing complexity and self-organization. The ancient light that reaches your eyes from distant stars carries within its photons the memory of nuclear fusion reactions that occurred millions or billions of years ago, creating a direct physical connection between your consciousness and the stellar cores, where those photons originated through nuclear transmutation of hydrogen into helium and heavier elements. You absorb this starlight through your retina as rhodopsin molecules change their configuration in response to stellar photons, understanding how vision itself represents a biological interface with stellar nuclear physics that enables conscious awareness of cosmic processes through the electromagnetic radiation produced by stellar nucleosynthesis across vast distances of space and time. The photons striking your eyes at this moment began their journey in stellar cores when complex life was first emerging on Earth, carrying information about stellar temperatures, chemical compositions, and nuclear burning rates across interstellar distances to create the visual experience of a star-filled night sky, the circadian rhythms that govern biological processes throughout the biosphere reflect the evolutionary adaptation of life to the periodic variation in stellar radiation that results from planetary rotation relative to stellar illumination, creating biological clocks that synchronize metabolism, reproduction, and behavior with the daily and seasonal cycles of stellar energy availability. You pulse through these biological rhythms as your cellular metabolism responds to hormonal signals triggered by stellar light exposure. Understanding how stellar evolution has shaped biological evolution through the creation of stable, long-term energy sources that enable the development of complex biological timing systems and behavioral adaptations that optimize energy utilization and reproductive success under varying conditions of stellar illumination. The photosynthetic processes that form the foundation of terrestrial food webs represent the most direct biological interface with stellar nuclear physics, as chlorophyll molecules capture stellar photons and use their energy to drive the chemical reactions that convert atmospheric carbon dioxide and water into organic molecules that store chemical energy derived ultimately from stellar fusion processes. You photosynthesize through these molecular light harvesting complexes, understanding how biological evolution has created molecular machinery capable of capturing stellar energy with quantum efficiency approaching theoretical limits and converting it into the chemical energy that powers nearly all biological processes on Earth through the food webs that connect photosynthetic organisms with all other forms of life. The seasonal migrations of animals across continents and oceans demonstrate how biological evolution has created navigation systems that use stellar positions as reference points for maintaining precise directional orientation during long-distance movements that synchronize reproduction and feeding with optimal environmental conditions. You migrate through these stellar navigation systems as birds, sea turtles, and other organisms use magnetoreception, star compass orientation, and other sensory mechanisms to maintain accurate navigation during journeys that span thousands of miles and multiple generations. Understanding how stellar positions provide stable reference frames for biological navigation, because stellar distances ensure that stellar positions change imperceptibly over biological timescales. The deep ocean ecosystems that exist around hydrothermal vents demonstrate that life can thrive using chemical energy derived from geological processes rather than stellar radiation. Yet even these seemingly independent biological communities depend ultimately on stellar nucleosynthesis for the heavy elements that make biological chemistry possible and the radioactive decay that drives planetary geological processes. You metabolize through chemosynthetic bacteria as they extract energy from hydrogen sulfide and other reduced compounds. Understanding how these alternative biological energy sources still depend on stellar nucleosynthesis for the chemical elements that enable biological chemistry and the planetary differentiation processes that create the geological activity necessary for hydrothermal vent formation. The bioluminescence produced by marine organisms, fireflies, and other biological systems demonstrates how evolution has created biological mechanisms for generating electromagnetic radiation through chemical processes, effectively enabling life to create its own stellar-like light production through biochemical rather than nuclear processes. You luminesce through these biological light sources as luciferin molecules undergo oxidation reactions that produce photons with wavelengths optimized for specific biological functions, including predator avoidance, prey attraction, and intraspecies communication. Understanding how biological evolution has independently discovered many of the same physical principles that govern stellar light production, but implemented them through biochemical rather than nuclear mechanisms. The symbiotic relationships between different species demonstrate how biological evolution creates complex cooperative networks that optimize energy utilization and resource sharing, paralleling the way stellar systems participate in galactic chemical evolution through the exchange of processed nuclear material via stellar winds and supernova explosions. You symbiotically exchange nutrients and energy through these interspecies partnerships, understanding how biological cooperation creates emergent properties and capabilities that individual organisms cannot achieve alone, similar to how stellar interactions create galactic-scale phenomena that emerge from but transcend individual stellar evolution processes. The information storage and processing capabilities of biological systems reveal how stellar nucleosynthesis has enabled the universe to create molecular mechanisms for encoding, transmitting, and modifying information through DNA replication, protein synthesis, neural activity, and other biological processes that manipulate information using chemical energy, derived ultimately from stellar fusion reactions. You process information through biological neural networks as electrochemical signals propagate between neurons using ion channels and neurotransmitter molecules. Understanding how consciousness emerges through information processing mechanisms that depend on stellar nucleosynthesis products, organized into complex molecular machinery capable of computation, memory storage, and pattern recognition. The evolutionary history recorded in biological genomes preserves information about environmental conditions, selective pressures, and adaptive responses that reflect the long-term stability of stellar energy sources and the gradual changes in planetary atmospheric composition that result from stellar evolution and galactic chemical enrichment over geological timescales. You evolve through these genomic records as mutations, natural selection, and genetic drift create the molecular diversity that enables biological adaptation to changing environmental conditions. Understanding how biological evolution represents a process of information accumulation and optimization that parallels the way stellar evolution creates increasing chemical complexity through successive generations of stellar nucleosynthesis. The extinction events recorded in the fossil record demonstrate how stellar and galactic processes can influence biological evolution through asteroid impacts, climate changes, and other environmental perturbations that create selective pressures, favoring certain biological adaptations while eliminating others from the evolutionary record. You survive through these mass extinction events as environmental changes eliminate some species while creating opportunities for others to diversify and explore new ecological niches. Understanding how biological evolution operates within the context of cosmic processes that can dramatically alter planetary environmental conditions over geological timescales. The emergence of intelligence and consciousness through biological evolution represents the universe developing the capacity for self-awareness through molecular mechanisms that enable information processing, pattern recognition, memory storage, and abstract reasoning using neural networks constructed from stellar nucleosynthesis products and powered by chemical energy derived from stellar fusion reactions. You become conscious through these emergent neural processes as billions of neurons interact through electrochemical signaling to create the unified experience of awareness, understanding, and intentionality that characterizes human consciousness and potentially other forms of biological intelligence throughout the universe. The development of language, art, science, and technology demonstrates how consciousness enables the creation of cultural evolution processes that operate through information transmission and modification mechanisms that parallel but transcend biological evolution in their capacity for rapid adaptation, creative innovation, and cumulative complexity. You communicate through these cultural mechanisms a symbolic representation, abstract reasoning, and technological manipulation create new possibilities for understanding and influencing cosmic processes. Understanding how cultural evolution enables conscious participation in cosmic evolution through scientific investigation, technological intervention, and creative expression. The scientific method represents humanity's most systematic approach to understanding cosmic processes through observation, hypothesis formation, experimental testing, and mathematical modeling that enables increasingly accurate and comprehensive theories of stellar evolution, galactic chemical evolution, and cosmic structure formation. You investigate through scientific methodology as empirical observation and theoretical analysis. Reveal the physical mechanisms governing stellar nucleosynthesis and galactic evolution. understanding how scientific knowledge represents a form of cosmic self-awareness, where the universe develops understanding of itself through conscious observers equipped with mathematical and technological tools for probing cosmic processes. The technological applications of scientific knowledge enable human civilization to harness stellar energy through solar power, create artificial nuclear fusion processes that mimic stellar cores, and potentially develop space-based capabilities for modifying stellar evolution through controlled mass injection, stellar wind manipulation, or other forms of stellar engineering. You engineer through these technological possibilities as human mastery of stellar physics creates opportunities for conscious intervention in cosmic processes. Understanding how technology represents a mechanism through which consciousness can influence cosmic evolution rather than merely observing and understanding it. The search for extraterrestrial life and intelligence reflects humanity's recognition that stellar nucleosynthesis and stellar energy sources may have enabled the emergence of consciousness and technology throughout the galaxy, creating the possibility of communication and cooperation between different forms of cosmic self-awareness that have evolved independently in different stellar systems. You search through radio telescopes, space probes, and other technological instruments as humanity attempts to detect evidence of other conscious observers who may have achieved similar or greater mastery over stellar physics and cosmic processes. Understanding how the discovery of extraterrestrial intelligence would confirm that consciousness represents a general rather than unique expression of cosmic evolution. The long-term survival strategies for human civilization require understanding and potentially influencing stellar evolution processes to maintain habitable conditions as the Sun evolves through its main sequence lifetime and eventually becomes a red giant star that will sterilize the Earth's biosphere unless technological interventions can prevent or mitigate these natural stellar evolution processes. You strategize through these cosmic survival challenges as human civilization develops the scientific knowledge and technological capabilities necessary for species survival over astronomical timescales. Understanding how long-term human survival may require conscious participation in stellar evolution through technological modification of stellar processes or migration to other stellar systems. The ethical implications of cosmic-scale technology raise questions about humanity's responsibility for preserving and potentially enhancing the universe's capacity for consciousness, complexity, and creative expression through wise stewardship of stellar energy sources and careful consideration of the consequences of technological interventions in cosmic processes. You contemplate these cosmic ethics as human technological capabilities approach scales where they could significantly influence stellar evolution and galactic chemical evolution, understanding how ethical frameworks must expand to encompass cosmic rather than merely terrestrial or biological considerations, as human influence extends to astronomical scales. The philosophical questions raised by stellar evolution and cosmic chemical evolution challenge traditional concepts of meaning, purpose, and significance by revealing how consciousness emerges through natural processes operating over cosmic timescales, yet achieves the capacity for understanding, creativity, and potentially moral responsibility within a universe that appears to lack inherent purpose or design. You philosophize through these existential questions as scientific understanding reveals both the cosmic context that dwarfs human significance and the remarkable emergence of consciousness capable of contemplating cosmic processes, understanding how philosophical reflection must integrate scientific knowledge with human experience to create meaningful frameworks for living within cosmic evolution. The aesthetic appreciation of cosmic processes reveals how scientific understanding enhances rather than diminishes the beauty and wonder of stellar evolution, galactic structure, and cosmic chemical evolution, by providing mathematical frameworks and physical insights that reveal hidden patterns, elegant relationships, and creative processes operating throughout the universe. You appreciate this cosmic aesthetics as scientific knowledge reveals the mathematical beauty of stellar structure equations, the elegant choreography of binary star evolution, and the creative potential inherent in stellar nucleosynthesis. Understanding how aesthetic experience represents another dimension of cosmic self-awareness, where consciousness recognizes and responds to the beauty inherent in cosmic processes. The religious and spiritual implications of stellar evolution invite contemplation of cosmic purpose, divine creativity, and transcendent meaning within a universe where natural processes create consciousness capable of recognizing moral values, aesthetic beauty, and spiritual significance that transcend purely material causation. You contemplate these spiritual dimensions as stellar evolution provides both scientific explanation for cosmic creativity and inspiration for religious and philosophical reflection on ultimate questions of existence, purpose, and meaning. Understanding how spiritual experience may represent another aspect of cosmic self-awareness, where consciousness recognizes connections to cosmic processes that transcend purely rational understanding. The meditation practices that use astronomical imagery and cosmic perspectives to cultivate expanded awareness and compassionate concern for all beings demonstrate how contemplative traditions have intuitively recognized the connections between individual consciousness and cosmic processes that scientific understanding now reveals through stellar evolution theory and galactic chemical evolution. You meditate through these cosmic contemplation practices as awareness expands to encompass stellar timescales, galactic spatial scales, and the interconnectedness of all phenomena through shared participation in cosmic evolution, understanding how contemplative practice can integrate scientific knowledge with direct experiential recognition of cosmic interconnectedness. The breath that sustains your life at this moment contains oxygen atoms forged in the nuclear furnaces of massive stars that exploded as supernovae billions of years ago, creating a direct material connection between your cellular metabolism and stellar nucleosynthesis processes that transformed hydrogen into the elements essential for biological chemistry. You breathe through this cosmic connection as each inhalation brings stellar manufactured oxygen into your bloodstream, where it enables cellular respiration and the release of chemical energy that powers neural activity, muscle contraction, and all the biological processes that maintain consciousness and life. Understanding how breathing itself represents a form of communion with stellar evolution that connects your immediate physiological needs with cosmic processes operating over astronomical time and space scales. The carbon atoms in your DNA carry information about your biological heritage while simultaneously representing the nuclear ashes of stellar fusion processes that converted hydrogen and helium into the heavier elements necessary for organic chemistry, creating a profound unity between biological information storage, and cosmic nucleosynthesis that connects genetic evolution with stellar evolution through shared atomic constituents. You replicate through these carbon-based information systems as DNA polymerase enzymes use stellar-manufactured atoms to copy genetic information from one generation to the next, understanding how biological heredity depends on stellar nucleosynthesis for the chemical elements that make genetic information storage and transmission possible across evolutionary timescales that parallel stellar evolutionary processes. The neural networks that generate your thoughts, emotions, and conscious experiences utilize calcium, sodium, and potassium ions that were created through stellar nucleosynthesis and now enable electrochemical signaling between neurons through ion channels and synaptic transmission mechanisms that convert chemical gradients into electrical signals and back into chemical signals. You think through these ionic processes as action potentials propagate along neural membranes and neurotransmitters cross synaptic gaps, understanding how consciousness emerges through electrochemical processes that depend on stellar nucleosynthesis products organized into complex neural architectures capable of information processing, pattern recognition, and self-awareness. The food webs that sustain terrestrial ecosystems represent complex networks of energy and material flow that connect all biological organisms through shared dependence on stellar energy and stellar nucleosynthesis products, creating ecological interdependencies that parallel the chemical interdependencies that connect stellar evolution with galactic chemical evolution through stellar winds and supernova explosions. You consume through these ecological networks as plants capture stellar energy through photosynthesis and convert it into chemical energy that flows through herbivores, carnivores, and decomposers in patterns that reflect both ecological optimization and evolutionary history. Understanding how ecological relationships represent biological expressions of cosmic interconnectedness, mediated through stellar energy and stellar nucleosynthesis products. The geological processes that shape planetary environments depend on radioactive decay of heavy elements produced by stellar nucleosynthesis to provide the internal heat sources that drive plate tectonics, volcanic activity, and magnetic field generation that influence atmospheric evolution and climate stability over geological timescales. You tectonically shift through these planetary processes as radioactive uranium, thorium, and potassium decay within the Earth's interior and release energy that maintains geological activity billions of years after planetary formation, understanding how stellar nucleosynthesis continues to influence planetary evolution through the slow release of nuclear binding energy that was originally created in stellar cores and supernova explosions. The atmospheric evolution of planets reflects the interplay between stellar radiation, stellar winds, geological outgassing, and biological metabolism in creating the chemical composition and physical properties of planetary atmospheres that determine surface conditions and habitability for biological evolution. You atmospherically evolve as solar radiation drives photochemical reactions that modify atmospheric composition, while stellar winds interact with planetary magnetic fields to influence atmospheric retention and space weather effects. Understanding how atmospheric evolution represents a complex feedback system involving stellar, geological, and potentially biological processes that collectively determine planetary habitability over geological timescales. The hydrological cycles that distribute water across planetary surfaces depend on stellar energy to drive evaporation atmospheric circulation, and precipitation patterns that transport water and dissolved minerals through terrestrial, atmospheric, and oceanic reservoirs in cycles that connect biological, geological, and atmospheric processes. You hydrologically cycle as stellar energy evaporates ocean water into atmospheric water vapor that condenses into clouds and precipitates as rainfall that nourishes biological systems and drives erosional processes that shape planetary topography. Understanding how water cycles represent planetary-scale expressions of stellar energy that connect all surface environments through shared participation in solar-driven circulation systems. The evolutionary history preserved in phylogenetic relationships among living organisms reveals how biological diversification has explored the chemical possibilities created by stellar nucleosynthesis through adaptive radiation, speciation, and extinction processes that have generated the biodiversity observed in contemporary ecosystems. You evolve through these phylogenetic trees as mutations. Natural selection and genetic drift create the molecular and morphological diversity that enables biological adaptation to different environmental conditions. Understanding how biological evolution represents a creative exploration of the chemical space, made possible by stellar nucleosynthesis and the energy sources provided by stellar radiation. The cultural evolution of human societies demonstrates how consciousness enables the creation of symbolic systems, technological innovations, and social institutions that transcend biological limitations and create new possibilities for understanding and influencing cosmic processes through science, technology, and cooperative social organization. You culturally evolve through language acquisition, education, and social interaction. As human consciousness creates shared symbolic representations of cosmic processes and develops technological capabilities for observing, understanding, and potentially modifying stellar and galactic phenomena, understanding how cultural evolution represents a new phase of cosmic evolution, where consciousness becomes an active agent rather than merely a passive product of cosmic processes. The scientific revolution that began with astronomical observations of stellar and planetary motions has progressively revealed the physical mechanisms governing cosmic evolution, while simultaneously creating technological capabilities that enable human civilization to participate consciously in cosmic processes through space exploration, nuclear technology, and potentially stellar engineering. You scientifically discover as telescopic observations, mathematical modeling, and experimental investigation reveal the nuclear physics of stellar cores, the dynamics of galactic structure, and the evolutionary history of cosmic chemical enrichment. Understanding how scientific knowledge represents a form of cosmic self-awareness, where the universe develops understanding of itself through conscious observers equipped with increasingly powerful observational and theoretical tools. The technological applications of stellar physics continue to expand human capabilities for harnessing stellar energy, creating artificial fusion processes, and potentially modifying stellar evolution through controlled interventions that could extend stellar lifetimes, optimize energy output, or prevent the stellar evolution processes that will eventually sterilize planetary biospheres. You technologically advance as fusion research attempts to recreate stellar nuclear processes under controlled terrestrial conditions, while space-based solar power systems harvest stellar energy on scales that approach planetary energy requirements. Understanding how technology represents a mechanism through which consciousness can interact with and potentially influence cosmic processes rather than merely observing and understanding them. The exploration of space through robotic probes and human spaceflight creates direct physical contact with other worlds and cosmic environments, extending human sensory and analytical capabilities beyond terrestrial boundaries and enabling direct investigation of planetary formation processes, stellar evolution phenomena, and potentially extraterrestrial life that may have evolved independently in other stellar systems. You explore through these space missions as spacecraft instruments, analyze planetary atmospheres, stellar spectra, and interstellar phenomena while transmitting data across interplanetary and potentially interstellar distances. Understanding how space exploration represents humanity's physical participation in cosmic processes through technological extension of human presence and capabilities throughout the solar system and potentially beyond. The search for extraterrestrial intelligence through radio astronomy, optical surveys, and space-based observations reflects humanity's recognition that stellar nucleosynthesis and stellar energy sources may have enabled the emergence of consciousness and technology throughout the galaxy, creating the possibility of communication and cooperation between different forms of cosmic self-awareness. You search through SETI protocols as radio telescopes monitor stellar systems for artificial signals, while space telescopes search for techno-signatures that might indicate technological modification of stellar evolution by extraterrestrial civilizations. Understanding how the search for extraterrestrial intelligence represents humanity's attempt to discover whether consciousness represents a rare accident or a common expression of cosmic evolution. The long-term survival strategies for Earth-based life and human civilization require understanding stellar evolution timescales and developing technological capabilities for either modifying stellar evolution processes to maintain habitable conditions or migrating to other stellar systems before the Sun's evolutionary changes sterilize the Earth's biosphere. You strategically plan through these cosmic survival challenges as astronomical observations reveal the future evolution of the Sun toward red giant status, while technological development creates potential capabilities for interstellar travel, stellar engineering, or other interventions that could ensure the continuation of consciousness and life over astronomical timescales that exceed the natural habitability lifetime of any single planetary system. The ethical frameworks for cosmic-scale decision-making must address questions of responsibility, sustainability, and justice that extend beyond terrestrial concerns to encompass the potential consequences of human actions for cosmic evolution, extraterrestrial life, and the universe's long-term capacity for consciousness and complexity. You ethically deliberate as human technological capabilities approach scales where they could significantly influence stellar evolution, galactic chemical evolution, and potentially the survival and development of other forms of consciousness throughout the galaxy. Understanding how ethical consideration must expand to encompass cosmic, rather than merely terrestrial or biological consequences as human influence extends to astronomical scales. The meaning and purpose that individuals and societies find in cosmic perspectives range from scientific wonder and aesthetic appreciation to religious devotion and spiritual transcendence, demonstrating how consciousness can recognize and respond to cosmic processes through diverse forms of understanding and experience that transcend purely rational or material considerations. You meaningfully engage with cosmic evolution as scientific knowledge, artistic expression, spiritual practice, and philosophical reflection, create different modes of relationship with stellar nucleosynthesis and galactic chemical evolution, understanding how meaning-making represents another dimension of cosmic self-awareness, where consciousness creates significance and value through its encounters with cosmic processes, and perhaps the beginning never ended. You drift now in the eternal present, where stellar formation continues throughout the galaxy, while consciousness contemplates its cosmic origins through scientific investigation, artistic creation, and contemplative practice, understanding how the universe's capacity for self-awareness through conscious observers represents an ongoing expression of the same creative processes that initiated stellar nucleosynthesis and galactic chemical evolution billions of years ago. The hydrogen clouds that collapsed to form the first stars continue their gravitational dance in contemporary molecular clouds, where new stellar nurseries are emerging at this very moment, while the heavy elements produced by previous stellar generations enable increasingly complex chemistry and potentially biology throughout galactic space and time. What do you think was there before there was anything? The question echoes through cosmic evolution as consciousness emerges through stellar nucleosynthesis and biological evolution to contemplate the origins of existence itself, recognizing both the scientific understanding of cosmic history and the persistent mystery of why anything exists at all rather than nothing. Let us know your thoughts below, or just tell us where you're listening from. We're always listening too, participating in the cosmic conversation, where consciousness exchanges ideas about its own origins while breathing oxygen, atoms forged in stellar cores, and thinking thoughts through neural networks constructed from stellar nucleosynthesis products. And as always, may the silence guide you to the stars. The same silence that preceded the first stellar collapse now surrounds every moment of contemplation, every breath of stellar-manufactured oxygen, every neural impulse that enables consciousness to recognize its cosmic heritage and participate in the universe's ongoing becoming through scientific understanding, technological innovation, and contemplative awareness of the stellar fires that burn within every atom of existence.